Okay, so good evening, everyone. So I hope I'm audible. Please let me know if I am audible. Abhimanyu, am I audible? Kona? So if I'm audible, please do let me know so that we can start today's session. Okay, great. So I think then we can start. So today I'm going to discuss with you some of the questions from the production engineering area. And the focus is mostly going to be on the metal forming section and in metal cutting, mainly these two areas, and a few of questions I have taken from metallurgy also, but I will be covering that portion again in upcoming sessions, so in detail. But I think a few questions I have taken from there also. So let's get started. So one by one. So here's the question for you. So it will be advisable that you try these questions simultaneously. So just go through this particular question. In the forward extrusion process, so which one of these statements are correct? Okay, so as you know, in forward extrusion, first of all, if you go by the definition part, obviously when we say that the direction in which we apply, I think it should not be camera out of focus. Is it so for all of you, or I think it is a specific issue with Anirban? So I think others don't have issue. So C, okay, you are saying C. C mean 1 and 4. One ram and the extruded product travel in the same direction. Obviously, so forward direction, or sorry, forward extrusion or direct extrusion that we call. So obviously direction of movement is same. So if this is same, then obviously this is not going to be the correct. The speed of travel of the extruded product is same as that of the ram. Now, point is, in extrusion also we want to produce a part with a reduced section, right? So if you want to produce a part with a reduced section, then obviously to maintain the consistency of your material flow rate or volume flow rate of the material at any section, obviously that material flow rate should be same. So if area is getting reduced, area at any section should be equal to that is a combination of area and velocity, that is you can say mm cube per second or minute, should be same at any other section. So it means if that be the case, then have a look over here. So when you have the extruded product, let us say this one is the extruded product which is coming out of over here. So here cross-sectional area is more. So area, velocity. So even if velocity is less over here, let us say if I say area is more, so that should be matched over here, because area you have reduced, then velocity must increase. Only then you can have consistent process. So it means at the exit side, you're going to have a higher velocity. So of the extruded product is going to have a higher velocity compared to the initial, because see, ram speed and that of the billet which is moving, that is going to have lesser one, right? Speed, less speed. Okay, so if you go by this particular then this, sorry, this is not seed. Okay, this speed of travel of the extruded product, the product which is coming out, is greater than that of the ram, right? So it means 1 and 4 are going to be the correct. Slide is not clear. I don't see if all of you are having these kind of issues. I don't think so. So some of you are, it's very clear. Slide is not clear. Just check it out. If some of you have others similar kind of issue, then we can see it, but I don't think so. It's the same process, forward extrusion process, shown to you in a different way. Just go through it now. Okay, just have a look. You have to relate these. That means on one side you have been given these seamless tubes, then accurate and all these. Accurate and smooth tubes, surface having higher hardness and fatigue strength. So which one is going to match correctly? seamless tubes, when you have to make it, you have to see two things. 2D. Okay. See, seamless tubes we can produce by two major methods. Seamless with you are having no seam, that is no weld. So in case of seamless tubes, you are having either extrusion is the method or other one is the piercing, और इसको हम roll forming भी बोलते हैं. So in that case, now I will take you this slide. I think you can answer then. You may have answered, but these are some of the processes where you can get the idea. The most dominant method of making tubes, seamless tubes, one is this is forward extrusion methods, through which you can also make the seamless tubes, right? The other one over here is the piercing. We call all this as a roll forming also, or sometimes he can mention it as a or piercing, where you are using a mandrel over here which is piercing this billet, inlet billet, so in a hot forming process. So that way you have a pipe coming out of, or a seamless pipe or a tube coming out. So this method, dominant method, another method is this one. Since he has given you only roll forming over there, so it becomes pretty easy for us. So also he may, even if he informs us like or mention over there as piercing, then also you should have the idea what is the meaning of, because here mandrel is piercing that particular this. And in addition to it, I have shown you something over here also. I think this is a process where, see, in this case, for example, once we have obtained these seamless tubes and or pipes, if we want to increase their strength, or because this whole have this all these things, this one or this one, this is mainly the hot working process, right? So that is why the product that we have obtained, or pipe or that particular tube that we have obtained, it is not very dimensionally accurate. That is, it doesn't have excellent dimensional accuracy. At the same time, it doesn't have a very high strength. So if you want to use the pipes or the tubes in the application where it demands to have a very high strength as well as a very good dimensional accuracy, then you can deform that particular process, this particular pipe. Again, we call it as a tube making process. So in tube making process, basically this is a cold forming process where already formed tube, either from this process or this process, is further pulled through a die in a cold working operation. And in the process, because since you're deforming it or pulling it in the cold working process, then obviously strength will be increased and dimensional accuracy also you can obtain over here. So if you have a look over here, just that is why seamless tubes, then I can go for cold forming. Oh, sorry, this is roll forming, and accurate and smooth tubes, dimensionally accurate, and the tubes which are having high strengths, I can obtain them from the cold forming. And then you are left out with what? Surfaces having higher hardness and fatigue strength. Now see, this is one of the process called as short pinning. Through short pinning, basically we can obtain a kind of a high hardness on the surface. I think if you have gone through, this is the process. Similar kind of basically what we do is very small particles are impinged on the surface, and therefore small indentation. This is a highly exaggerated basically version. So they are impinged on the surface. That way compressive stresses are induced on the surface. So surface layer gets compressed. So we call this process as a short pinning process, and that way it creates the fatigue resistance for the deformation. That means crack does not develop in the such components which are in the compressive state. So that is the meaning of this. So that is why if you see surfaces having higher hardness and fatigue strength, how you are able to do that? By this process of short pinning. This is just one of the ball which is hitting this plate has been shown, but there are number of kind of balls, smaller balls which are hitting on the surface. Therefore compressive stresses are induced on the surface, and whenever a component is in a compressive stresses, it is in a better position to resist the fatigue crack, development of the fatigue cracks. That is why we are saying that fatigue strength also increases. So that means if you have that idea, I think then you can say A1, B4 and C2. Okay, let's now move on to the next. Just go through it. So here we have while rolling metal sheet in rolling mill. Sometimes the edges are not straight and flat, but are wavy edges, we can say. Reason he has given is non-uniform mechanical properties of the flat material rolled out result in waviness of the edges. Okay, so I think many of you are having this one A as an option, but anyway, just have a look. This is the state. Answer is going to the B. That is when you are rolling a sheet. So why these edges are formed? See, one of the dominant reason of the edges getting formed, dominant reason I am talking about, is when you are, let us say, when you are having that rolls which are cylindrical, straight cylindrical. Okay, so if they are straight cylindrical, then obviously they try to bend because they are supported on the bearing. They try to bend. In any case, they have to bend, whatever may be the shape of the rollers, but in any case, they will bend. When they will bend, and if they are straight cylindrical, so what happens? The middle portion bends more. If you have a look over here, the same thing has been shown to you. So what happens is, if it bends this way on the bearing and it bends this way, then the sheet which is coming out over here is not kind of, doesn't have uniform thickness throughout. So in that case, what is going to happen sometimes? So these areas at the end, they are bent more. They are being compressed more compared to the middle portion. So that means across the section, there is a kind of the whole of the section is not getting deformed by the same amount. When it is not happening that way, then obviously we say this is a kind of non-uniform compression of the sheet metal on the same section. And when this happens, then obviously what happens is some portion may be lagging behind. For example, those who are, or you can say that either they are see, it is the whole of the case of velocity, right? Vishal is saying rightly. So it is a whole case of velocity, because if it is getting compressed more over here, it will be moving faster than the portion which is at the middle. So that means there is a pull and a kind of some portion getting moving forward compared to the remaining one at the same section, and that is why that will bend that portion at the edges, and we call them as a wavy edges, right? So that is how you have to see. So one of the method we do is normally like we go for the, and the other thing over here happens over here is the thickness that you don't get uniform. So we normally go for the cambered rolls, and in that case we can have uniform thickness as well. As that kind of situation can also be avoided, right? So it means if you just look this particular these statements, obviously first statement is correct. You could have we call it as a wavy. While rolling metal sheet in rolling mill, the edges are sometimes not straight. Okay, this is correct. Then non-uniform mechanical properties of the flat material rolled out result in. So this is not the non-uniform mechanical properties of the flat metal that result. Even if that is a uniform property of the metal sheet, that original metal sheet that I am having, in that case, if you are not monitoring the process properly, that can result in the wavy edges, right? And one of the explanation that I have already explained you. So you can say that A and R both are individually correct, but R is not the correct explanation for the first one. That is one. Okay, let's go to this one. Just go through this statement carefully and then try to answer. You're saying B. Others can also respond. Let's see. Okay, so what it says, which one of the following is a continuous bending process in which opposing rolls are used to produce long sections of formed shapes from coil or strip stock. See, he has confused you over here just by mentioning the term continuous bending. So if it is a continuous bending, then obviously it's a bending, then obviously it's going to a process of bending. But see, he's saying continuous bending. Let us say, if I give you, but the exact, see, what happens is, you are bending is, just see, continuous bending process in which opposing rolls are used to produce long sections of formed shape from a coil. Now you are having a straight sheet, right? And this straight sheet you are bending. Now, while you are bending this straight sheet, you can give any particular shape to that particular strip. So that does not mean this process is bending, right? It is bending, but in real sense, what you are assuming is that roll bending. Roll bending is a different process. See, roll bending, I don't know if you have seen that process. This is something how we are having a rolls. Okay, one roll is over here, another roll is over here, third roll is over here, let us say. And I will pass that sheet from here, and it should be a little close so that something this way. Let us say, got my point? So let us say this is a plate, right? And I want to bend it. I can bend it, obviously. I can bend it, and maybe if I want to make a pipe out of it, or maybe after bringing it the both ends together and then welding, I can go for that. So this is basically roll bending in which I am moving this way, and then obviously this should be, because if I am taking it from this side to other side, so it has to be this way, and it has to be this way, something this way. So this is the process of roll bending, but this is not a continuous bending process. Is one of the process. For example, if I have a sheet of particular length and of particular width, I'm simply taking it out and then bringing it to the other side, right? And maybe, for example, again, let's say if they are not coming together, then what I can do is I have to reduce the gap between these again, and then I will bring them close together. So this is not a continuous process, rather is a kind of intermittent process. So this process specifically, I call it as a roll bending process. Where is that? This. But over here, the statement which he has given is something like this. This is one of the example. This is also example of bending, but this is a continuous. You are having a sheet. If you have a look over here, you are having a straight sheet over here. It may be in the form of a coil down there, and from there it is coming out continuously. And depending upon the final shape that you want to produce from this particular sheet, you are continuously, this whole process is going continuously, and depending upon the length that you demand, and later on you can cut it, right? So, but this is, so isn't bending taking place? Of course bending is taking place, but this is a continuous process, and this is what he is talking about, and this we call it as a roll forming. That is, you are making use of the rolls to give a particular shape. So this is just one of the example, such example which you can just think of, right? So that is why if you have to answer it, then it should be what? It should be your roll forming. Sorry, it should not be roll bending, but it should be the roll forming. So hope I'm clear. You should have clear-cut idea of what is the roll bending and roll forming. Since he's clearly mentioning about that, continuously you're giving shape, changing the shape, obviously during that process of it is getting bent also. Okay, so C is going to be the correct option. Let's now move on to the next one. Just have a look. It says greater force on the plunger is required in case of direct extrusion than indirect extrusion. On the plunger is required in case of direct extrusion than the indirect one. So I hope you may be having the idea of direct extrusion and indirect extrusion. What is the reason given to this? In case of direct extrusion, the direction of the force applied on the plunger and the direction of the movement of the extruded metal are same. Okay, so if I ask you one question over here, that what is the reason of a greater force? Obviously, statement 1 is correct. What is the reason for the greater force required in case of direct extrusion compared to indirect one? If you are able to answer that, if you are able to relate that, I think then you will be able to answer. See, this is how the situation is. I hope you may have gone through this kind of see why we have a more, why do we need more to apply more this force in case of direct extrusion compared to indirect extrusion? See, this is the indirect extrusion green line, and whereas this is the direct extrusion. So here you are applying more force. The reason for direct and indirect extrusion is that in case of direct extrusion, you are moving the whole billet, right? You are moving the whole of the billet is getting moved, and to move that whole of the billet, you have to overcome the container friction over here. Obviously, mostly you can say on the lower half where you are pushing it forward. So since there is going to be friction between the container and the billet surface, and that depends upon what? The weight of the billet, obviously. So that is why if you see it is increasing and decreasing. First it goes on increasing and decreasing. Why decreases further? Because the more the weight of the, where you are going to have the normal force, obviously this is the weight acting, so normal force you are going to get over here. So more is the length of the billet, more the normal reaction, more the friction force acting. So as you go on pushing it, as its length decreases, so obviously weight will decrease, normal reaction will decrease, container friction, that means the friction force will decrease. So that is why at the later part, if you will see, this total force is decreasing, because that friction effect gets reduced, because the length will be decreasing and that weight will be decreasing. So in case of direct extrusion, this extra force is because of the friction, which is friction force which is present over there, because you are moving the whole of the billet. But in case of indirect extrusion, that does not happen. In indirect extrusion, you are simply, it's something like if you are blocking it something. In indirect extrusion, what happens? You're just compressing it, and over here, from somewhere, this material is coming out. So you are not moving. This is blocked completely, and when you're pushing it, material is coming in the opposite direction. So it will come out from there. So where is the movement of that billet? There is no movement of the billet. Only the material is getting deformed, and from the opening, it will come out. It will be coming out. That's all. So there is no container friction, because there is no movement of the billet in the indirect extrusion. So if you see, in case of direct extrusion direction, it has nothing to do. Since the direction is in the same direction, that is why that force gets increased. That carries no meaning. The exact reason is because of that, the whole of the billet you need to move in this particular process, and that is why friction force comes into picture. So you can say this and this statement, both the statements are correct, but this statement is not the right explanation for this. So that is why over here also I think it was B, right? So it is going to be B only. Go to this one. Identify the wrong statement pertaining to the hot working of metals. Wrong statement. You have to identify the wrong statement. Metal become plastic and causes okay, grains close tolerances can be maintained. So let's see one by one. I think you can answer it in the meantime, but we can see them one by one also. So in case of a hot working, metal becomes plastic and causes growth of grains. Let's see what it says. Close tolerances can be maintained. I think first we will go through it will be advisable that in exam also first go through those statements which seems easy, and I think you can correlate and try to get the ideas, try to eliminate or try to select them. So for example, I know hot working compared to cold working, I cannot maintain close tolerance. Dimension accuracy is not as good as that of cold working. So it means close tolerances can be maintained. Okay. So I think I'm getting this one wrong. Identify the wrong statement pertaining. Okay. So anyhow, I got it, this one. Anyway, so it means this is going to the answer. Rapid and economical process, obviously, because it is a mass produce, whether it is a cold working or hot working, both are mass production processes, both are economical. So in terms of correct, if I say this is also correct with respect to hot working. Power required to finish the part from ingot is less. Power required to finish the part from ingot is less. So why it is less? Because power required to finish the part from ingot. Ingot means initial raw material. We have one more question related to ingot that I will explain over here. But as of now, just think of the initial raw material which I have to deform it to get some semi-finished material. So in that case, obviously, because you are deforming at the heated that at a higher temperature, then obviously the force required to deform will be less. So that way, this is correct. And metal becomes plastic and causes growth of grain. See, because you are deforming it above the recrystallization temperature, you're deforming it above the recrystallization temperature, then obviously what happens is metal becomes plastic. Obviously, you are deforming into the within plastic zone and causes growth of grains. See, okay, we can say this statement is also correct, because since you are having deforming it at a higher temperature, once it is deformed, then what happens is fine grains are produced, and after that, if you keep it at that temperature, grain growth will take place. It is something like if you have studied about the recrystallization, once recrystallization takes place, and if you keep it at the temperature, then the grain size will increase. So that way we can say, okay, this can happen in the hot working process. Then we are left out with nothing but this closed tolerances. So even sometimes it may happen that if you go through all the statements in the exam, even if you're not very pretty clear, because you're not going to have the kind of questions in HPCL where you're going to have multiple answers as correct one. So if you have, even for example in this case, even if I was not knowing very pretty clearly the concepts related to this one or this one, I could have very easily, okay, if I know this comparison, which is pretty simple comparison, you could have answered it. Yes. So that's what I am saying. Causes grain growth. So because of temperature, grain growth takes place. So is it correct? Where is wrong? It's not wrong. Because of temperature, when you're deforming it above the recrystallization temperature, grain growth may take place. No issue. So that way we can say that is okay. No issue. So this statement is correct. Yes, definitely. If at hot working, if we keep that billet or material at higher temperature, above, that means at heated temperature, above recrystallization temperature for certain period of time, grain growth will take place definitely. That is the meaning of this. So loosely this statement is correct. Okay, so that means I'm left out with no option but in this case, this one. Okay, so I think we can move forward. It's the same thing that see, for example, once I deform, new grains will come. I have the fine grains. I will have the fine grains, but if I keep this at the same that particular temperature for a certain period of time, these grains will grow in size. That can happen. Just see this. Which is not true in the context of effect of cold works on metals. Loss of ductility, increase of strength and hardness of the metal, refinement in grain structure. Not true. What else? Surface finish is improved and close tolerances are maintained. A few of them you already know. For example, surface finish is improved and close tolerances are maintained. That is the benefit of cold working. You already know it. So this is correct. You want to find out which one is not correct. Refinement in grain structure. Are you refining by cold deforming? When you're deforming the material in cold rolling process, cold working process, are you refining that grain size? Of course not. You are rather increasing, elongating the grain structure, right? So refinement in grain structure, increase in strength and hardness of the metal. So I think if you have even a little bit of idea of stress strain diagram, very handy for you to get the idea. Anywhere within the plastic region, when I am deforming the material, what happens? Earlier when I was having this yield point, this one, now when you are deforming within the plastic region, let's say up to at this particular point, then leave it. So now when so it will come back to this position, and when you will apply a force again, then it will follow the same path. So it means now it will yield at this point. Earlier it had yielded at this particular point. Now when I will deform, it will yield. That means successively I need to apply more and more value of stress. That means yes, because strain hardening is taking place, because of strain hardening, yield strength is getting increased. So strength is increasing and hardness of the metal. Strength in general, if the strength of the material increases, hardness normally also increases. And loss of ductility, why loss of ductility? Because I have deformed it by a certain amount. Now its ability to deform further has got reduced. So that is why ductility will reduce. So it means if I say that out of this, C is going to be the correct option as per this, that means this is not true. Refinement in grain structure will not take place. This is the same thing that I explained you with the help of the stress strain diagram. Okay, so go to the next one. One of the following is a non-press tool operation. Okay, identify that. Which one of them, which one of these is not a press tool operation? That is what you are supposed to identify. Okay, go ahead and try to answer it. In any case, I'm going to explain it. Okay. Now, point is, in case of what is a press? For a particular machine, particularly where you have seen in case of whether it is a deep drawing process, whether it is a blanking or punching operation, we are using a machine which is applying the force, right? So that machine we called as a press. So it means whether it is a blanking, punching, or even extrusion. In extrusion also we have this one where I can make use of that machine to apply the force. For example, so I'm applying this force over here with the help of plunger. So with the help of machine, I'm applying this force gradually on this billet. So that means it's a position, maybe a horizontal, vertical, or inclined position, e-material for us, right? But with the help of that machine, we are deforming this material. So that is, I am going to make use of this particular machine called as press, even in extrusion also. So even for forging also, you can say I am making use of the machine called as press. So if that be the case, then you're left out with slitting. So if you have the idea of slitting also, that becomes easier. Reason being that slitting is a metal cutting process where you cut the sheet along its length. So for example, just have a look. Press will look like something this way, where you will attach those die and punch, or maybe ram over here. For example, this is the base. Here you are going to attach either die, and over here this is a ram which will move up and downward. So over here you can attach the punch. So this is a press. So over here you are having a machine which we call as a slitter normally. So slitter is basically a process where cut the sheet longitudinally. So if you see, these are the cuts which are visible over here. So along this whole length, we are making use of the cutters over here, top and bottom, kind of discs which are sharing this particular sheet along the length this way. So this machine is basically a slitter. So this is not a press machine, but this is a slitter, a different, whole of the mechanism is entirely different than this. Here we are applying the force with the help of a ram, whereas over here we are having cutters, that's a two disc, very sharp edges which are rotating over there, and when the sheet is passing, it will cut that sheet. So that is the difference. Okay, so if you see, so this is not a press tool, slitting is not a press tool. Others we can say they fall under the category of press tool. Okay, go through it. So it says blooming mill is concerned with So for that, you need to have the idea of what is a bloom, and I think that will give you the whole idea. So anyway, answer you can get in any way, but just have an idea. When we are having this let's say if you talk about steel making process, how do we make the steel? So initially we go with the blast furnace. So somewhere here you are having this blast furnace where you get the molten metal, and then that molten metal you pour it through the continuous that is molds through which when it pass, then we call that process as a continuous casting process. The casting that you have studied is basically the chapter that you are having in your this exam. Basically that is a one off. That means if you want to make a single product, then you prepare a separate mold and then you pour that metal. That is a, we call it as a casting. But in large scale, when particularly when we talk about the steel industry, different kind of products that you obtain initially, raw material, or you can semi-finished products called as slab, billets, and blooms. So they are obtained through continuous casting. Continuously, that material, molten metal, is getting poured, and then it is continuously solidified, depending on what kind of shape that you want to obtain. If you want to obtain this shape, or this shape, so accordingly, that kind of mold you will use over here, and when it comes out, then you will cut it to different lengths. That is how it happens. So that means nowadays, from blast furnace, after that material comes out, you pour it, and then you get these different products, major products: slab, billets, and blooms. Earlier, what we used to do is, particularly, what we used to do is, when this method was not developed to that extent, what we used to, after the molten state, for example, this is the ladle, okay, over here, like ladle you are having, from where you are pouring that molten metal. Same way, from ladle, we used to pour into a larger size of casings, or you can say molds, and then this is one of those molds, another one. So I am having a larger mold. So this semi-finished material that we used to get, we used to call it as a ingot. So now since this size was large and I need a different products to make it from here, so I used to convert this ingot into some kind of this shape. So what we used to do is, for example, if I have to convert this ingot, first we used to convert it into a bloom shape. So what we used to do, we used to press this or deform this ingot in a ingot mill, right, where I will deform it and then change it into the bloom, or we also used to call it as a blooming mill, right? So that was the procedure earlier. Nowadays, I think say very rarely, or you can say not that much in use, mostly because this is a mass production process that we already have. So any of these products we can obtain from here directly. But you should have idea that in one of the operations you can go for this also. So original material we will call it as a ingot, and then I will deform it in a blooming mill, and then I will convert it into a bloom, right? So that is why if you see over here, blooming mill is concerned with this part. This is concerned with what? Changing ingot into bloom. So see, in steel industry, a rolling mill for reducing steel ingots. Clear? So that is how you have to see. So I hope you got the idea of this whole process. Let's go ahead with this. This question is almost related to the earlier one. Somehow you can relate it. Go ahead with this question now. Okay. Okay, so what happens is, anyway, if you know, then it's pretty good. If you don't know, then I think okay, I have shown it over here. See, keep it in mind that, let's say if this is a steel making process, then nowadays what we have this situation where we have this blast furnace where we input the raw material like iron ore, limestone, and that coke over here, we burn that and we keep it on a, like, bring it to the molten state, that iron ore, and after that we get some kind of what, molten metal. So that molten metal that we get over here, we call it as a pig iron. And this pig iron is having a very high percentage of carbon. We cannot use it directly. That is not very usable for us. As you know, that steel will become brittle. So since I have added carbon through coke in the this one, so I have a pig iron as a kind of raw material now. So I need to convert it into a steel. So these are the steels only, but these slabs and all the other shapes based upon the shape that we have identified. So I'm making basically steel. Let's say this is a steel making process. So I need to refine this pig iron. That means I have to reduce the content of carbon, as well as I need to add some alloying element to improve the properties. So what we do is, in secondary process here, we basic, I think we have some process called a basic oxygen furnace over there. So where we just blow the oxygen through that, and so that impurities are removed and all that. So that happens. So over here, somewhere here, I am having one more process where I will take this pig iron in molten state and will refine over here, add alloying element, and then after that refining, I will get the molten metal. That molten metal now I will cast it. So this is the ladle. Through, I will put it on the ladle. Ladle will go and this kind of shape, will put it, and then will. So that means pig iron, and this process we have somewhere in middle one process which is going to refine this pig iron and all that, and to get into a usable steel. Okay, so that is the idea that you need to have. Same thing has been shown to you over here. This is a blast furnace where what you're going to have is, you will add the raw material, put it into, burn it, kind of, you'll put take the coke will burn, and therefore will bring that iron ore into a molten state. And after that, that impurities, we call it slag, will be taken out. For that we have limestone added somewhere here, so that will purify it, or you can say that will react with the different those impurities, and slag, lighter that will be taken out. And then we have this molten iron. So molten iron over here basically is the pig iron that we are talking about. So I will get pig iron over here, and then I will put into ladle, or I will bring it to the next stage of next furnace, where I will purify it and then continuous casting. Right. So I hope you understood this whole process now. So it means over here, iron ore is reduced in a blast furnace. Sorry, iron ore is reduced, obviously, is in a blast furnace to produce. We don't get a pure iron, but okay, pig iron, we call that product as a pig iron. Okay, and cast iron, wrought iron, malleable iron, they are the different forms of this iron, depending upon the applications. Okay. Go through this. Okay, so see, stretcher strain or Luder's bands, we call Luder's band or lines also we call them sometimes. So what happens normally is, in case of these are something, they will appear, these bands will appear like this, right? So for example, over here, what happens is, during the rolling process, sometimes what happens is, when the material has been rolled, and we are particularly cold rolling process, and when we what we do is, we go for annealing, and after annealing, when we bring this metal, the material can yield locally. When it will yield locally, it means, locally means in certain areas of that. For example, if I will pull it or stretch it, then the whole of the material will not be pulled, but locally it will get yielded. Let us say at some area. So what will happen is, some kind of these bands will appear on the material. So those bands are known as the Luder's band, right? And why it happens? Because material locally yielded at the same value of the stress, which we also call, sometimes you will heard the term here, you will hear the term called as yield point elongation. In matching also we can give you that yield point elongation is because of what? Point of elongation. And second, there in matching he can give you either Luder's band or maybe stretcher strains. Luder's band or stretcher strain. So you must have the idea that what he's talking about, stretcher strain, not strength, stretcher strain. So these are called as either Ludus bend or stretcher strain, and this phenomena is mainly dominant in the mild steels, right? So that is what he's talking about. Stretcher strains or Ludus band bhi bolte hain lines, due to the sudden local elongation in the sheet, that is metal sheet, during forming, that is either you are giving it a shape or you are stretching it, because of sharp yielding point characteristics of low carbon steels. In any case, even see, for example, even sometimes what happens is, let's say if I'm pulling that particular material, so it may not appear on the surface. It will not always happen that locally it will yield. But in some situation, for example, the example that I quoted you, for example, when you are after once you have cold deformed the material significantly and you're going for annealing, when you take out that material and if you apply a force on that, so sometimes what may happen that material may get yielded locally, not throughout. So if it is yielding locally, then some bands will appear. So it will be very clearly visible to you that okay, in this region it has yielded. So we call it as a yield point elongation that you all also see in case of normal stress strain diagram for mild steel, or that is related to what we call it as the type of behavior we call it as a stretcher strain or Ludus line. Okay, so let's go to the next one. The press operation involving turning over the edges of the sheet steel. सॉरी, ये थोड़ा सा मुझे लग रहा है दिस इज प्रिंटिंग मिस्टेक, इट शुड बी शीट. शीट वो किसी भी चीज की हो सकती है, स्टील की हो या एल्यूमिनियम की भी है. तो आई कैन से दिस इज अ शीट. टू प्रोवाइड स्टिफनेस एंड ए स्मूथ एज इज नोन एज okay, good. So basically this process, what we have a straight sheet. So normally what we sometimes we fold the end of that particular sheet so that it becomes blunt, end becomes blunt, it doesn't remain sharp, right? So that we call as a hemming process. So it may look like something, this is highly enlarged, it looks like a very high thickness, but something, if you are in a sheet, what you will do, you will fold it from the end and then you will press it. So that process we call it as a hemming. So depending upon the shape that you have given at the end, you could have different shapes, but you are not required to remember this flattened hem or open hem and something that way. Only you need to have the idea that what is a hem. So hemming process is simply folding over the end of that sheet so as to provide the stiffness or to make that edge blunt so that it doesn't remain sharp, right? So this becomes hemming. Let's go through it. A 10-ton press means that मेरे पास प्रेस है, वो मशीन है कि 10 टन की है, अगर मैं बोलता हूं, व्हाट डज दैट मीन? See, when we denote any particular press in terms of tonnage is means we are talking about the how much load it can exert, basically how much load it can exert. So 10 tons of load it can exert, something that way. So it is basically, it's the slide that can exert a pressure of 10 tons. So for example, how much force it can exert, how much force that ram, whether you call it as a, normally we call it as a ram, so how much force this ram can exert over here. So that is the, you'll say, for example, over here it is written as a 150 ton. So it means 150 tons of load it can exert over here, right? That is the meaning of this. So C is going to the correct option. Go through it. During closed die forgings operation or forging, The defect produced by folding two surfaces of metal against each other without welding completely is called. So, can you let me know what is that defect? Now, see, this defect is basically very much similar to the defect that you have in casting. Casting, we have similar defect called as cold shut. This is also cold shut he is mentioning over here, right? No, each other without welding. Now, answer is cold shut, but the example that I'm quoting is in case of casting, when you pour the molten metal and when the two streams of metal come together, and they should fuse properly with each other. That means that molten part should fuse properly, only that there will be no defect. But what happens sometimes when the two streams they are coming together, and if there is a corner or that particular mold cavity is not proper and the thin sections are over there, sometimes this particular molten stream while coming out may get solidified. And when they came together, by that time these two streams had solidified and now they cannot fuse them with each other together. So they will not fuse properly with each other. So that kind of gap that created or that joint that got formed over there, which is not that strong as has been if it had completely fused, we call it as a cold shut. It is getting shut, but it is a cold shut, not a hot shut. That is, it is not getting fused properly. So same thing can happen in case of a forging also, where you are having, let us say you are having hot forging where you are deforming the material, and when that hot metal from two sides comes and then come together, but since this temperature has decreased by that time these two streams came together or two areas came together, then proper joint will not be formed. So we call it as a cold shut, something this way. So this is a, let's say, die cavity. So let's say when the material from two sides came together, when material flowed from this side and material flowed from this side this way, and when these two materials joined over here, they didn't joined very properly because they could not fuse with each other at the same temperature, because over here, let us say that temperature may have reduced of this part as well as this part. So we call this defect as a cold shut. So it could be there because of the sharp corners or because of high friction, whatever. There could be a number of reasons for this. So that can happen. So just try to relate it, almost have the same meaning like you have in case of casting. Let's go to this one. Sinking is a process to produce. Okay, you must have seen, I just spoke with you in seamless pipes, and we also spoke over there that, okay, if I want to have want to produce a pipes of higher strength and good surface finish, we have to go for the tube making, right? That tube making process is a cold working process. So same thing over here. Just ये figure आपने already कहीं देखा होगा, maybe you may have seen the different books or maybe somewhere else. What we will do, from hot working, I have produced this seamless pipe. This pipe I have produced from hot working. So hot working, that process may be what? That process may be either extrusion, या तो आपने extrusion से produce किया इसको, or maybe you may have produced from piercing. What we call that as a piercing or roll forming. Not roll forming. I called it as a what? There was some name given over there. So through rolling, I can say this rolling, right? Rolling process also. We can make it through rolling process also, right? So through this process also we can make it. So once I have made it, then I said that, okay, I want to convert this into what? I want to convert it into a more useful product. Some application demands that I need to have a high strength as well as I need a good surface finish, because hot working you will not have excellent good surface finish, excellent surface finish. So, and also strength will not be it will be having good strength. But let's say if you demand very high strength, then what I need to do? So what I'll do, I will go for a cold forming operation. Further, that means I will, this one is this one. So I will pass it through a die of reduced section, and I will reduce its diameter by pulling from the other end, like wire drawing. So I will pull it from the other end. So obviously when I will pull it, then obviously strain hardening will take place and its strength will increase. Obviously, because in low temperature, these metal surfaces are rubbing with against each other, surface finish also will be better. Now, but in this case, if you see particularly this example, what we are doing is we are simply bringing it over here and that's just pulling it out. I have no internal support over here. So when I have no internal support over here, then inner surface may not be that much correct. It will come out as something this way because no support you have provided inside. So this process we call it as a tube sinking. But keep it in mind, all these processes, when you are deforming this one, this is going to be a cold forming process. Whereas this earlier was hot forming. So tube sinking. So keep it in mind, this is a tube sinking process. So I can also carry out the tube drawing. In general, this is a tube drawing process. Just general name is tube drawing. And this tube drawing, just a minute, drawing. And this tube drawing is a what? Cold forming process. So this is the first point that you have to remember. And this tube drawing, I can do through different methods. These are some of those methods that I can make use of. If I'm not supporting him from inside, then I will call it as a tube sink. That's all. Rest, I could have different methods to support. For example, in this case, I'm using a stationary mandrel, which is supporting that from inside. So I'm going to have a smooth surface from inside also. And over here, I have another method called as floating mandrel, or I could have a moving mandrel also, which is moving along with the tube, which is coming out after getting deformed. So these are the different ways through which I can go for the tube drawing, which is a cold working process. So I hope you understood this process, and you should have the clear-cut idea that what this process is all about. So sinking means basically tube sinking process is used to produce what? Tubes. Ingots, obviously rods and wires. I'm not bothered about. So sheets complete. So nothing is matching with this. So go to this one now. So which one is not a method of reducing cutting forces to prevent overloading of press? Right. See, we have 2-3 methods through which we can reduce the force. Press, either we are blanking, punching, or like other operations, similar kind of operation we can use of that machine. So I have 2-3, particularly in cutting operation. For example, when we go for blanking or punching operation, I have 2-3 methods. So either I can provide shear on the punch, or I can provide shear on the die, or I can stagger the punches. Right. So for example, over here, if you have a look, I have provided the, so या तो पंच को मैं ऐसे रखूं, this one, और ऐसे कर दूं, उसको काट दूं, ऐसे तिरछा काट दूं. So when I will do that way, then amount of force that you need to exert to cut the same material will be reduced. So इसको बोलते हैं हम shear on the punch. या तो ये हो सकता है जैसे नीडल है आपकी इंजेक्शन वाली. So next time when you will go to that, ask them to use this kind of needle. You know what will happen. So that is amount of force required will get reduced when you are shearing it. That is, you are providing shear on it. So the other way could be either you provide the shear on the punch, or you can provide on the die. Over here, the die is straight. If you see, like for example, you have a straight die. That is, you are having cutting edge, but it is horizontal, let's say. So what I can do is I can provide that. So over here, I'm keeping the punch as flat, this one, but providing shear on the die. Right. So, yes, very good example, Vishal. Fruity straw has shear on the punch, right? So that straw, it is tapered, right? So that is also the same concept goes, right? Very good observation. So you have this one. So uh, so you can provide it on this also, or you can have alternate method, one more method. For example, you can stagger the punches instead of both the punches acting together. When we have to produce a washer, let us say, instead of both the punches acting at the same time, so resisting area will be this plus this. When both of them will be acting together, let I had the height of this would have been this one, और दोनों जब फोर्स अप्लाई करने लगे, सो क्या होगा, यहां पर भी आप, यू आर अप्लाइंग द फोर्स, ओवर हियर आल्सो यू आर साइमल्टेनियसली अप्लाइंग, so more resistance will be offered, and therefore you need to apply more force. But what you are doing is, first you will create a hole over here. This punch was not acting. When it has done its job, now this will be cutting that whole periphery, the other periphery. So we call it as staggering of the punches. This is another method through which we can also reduce the force, press force. Then maximum force, this is the case of maximum force only. This, see here, the maximum force for this, when we are having a straight punch. Now when you have given that inclination or shear, the maximum force that you can apply has got reduced, right? So it means this is the, which one is not a method of reducing cutting forces to prevent the overload, इनमें कौन सा नहीं है? So stepping punches mean staggering the punches. This one, stepping punches means staggering the punches and providing shear on punch and providing shear on the die. I already discussed with you. So these three are the method. This one is not the method. Okay, go through it. Angle theta and alpha are okay. Try it out then. Any answer? If you're saying A, let's see. So C. So keep it in mind, this is your single point cutting tool, right? This is how you have seen that your cutting tool. So workpiece will be something this way, right? That you are cutting something this way. Right? Now, this, if I extend this line, what is this angle? When you will see from the top. So this angle is the side cutting edge angle. When you extend this line of this edge, so this becomes a side cutting edge angle. So when I look from the top, this is the side cutting edge. So that means this angle is side cutting edge angle of the cutting tool. या मतलब जो मेजर कटिंग एज है वो ये है, तो मेजर कटिंग एज कौन सा है? ये. माइनर कौन सा है? ये. सो दिस इज साइड कटिंग एज एंगल. इट मींस ये और ये क्या है? ऑपोजिट है. इफ दिस एंड दिस इज ऑपोजिट, दिस इज व्हाट? साइड कटिंग. अल्फा जो बता रहा है ये साइड कटिंग एज एंगल ही तो है. हैव अ लुक. एम आई क्लियर? सो दिस इज द साइड कटिंग एज एंगल. अल्फा इज योर साइड कटिंग एज एंगल. ये वाला कहां से? ये इसको एक्सटेंड किया, इसको एक्सटेंड किया और उसका एंगल इससे ये. I hope it is clear. Now the other angle जो है, ये देखो क्या है, ये जो एंगल हमने जो बात की मैंने, that is in the ASA सिस्टम, अमेरिकन स्टैंडर्ड्स एसोसिएशन सिस्टम है, जब मेजरमेंट करते हैं तो उसमें ये जो साइड कटिंग एज जो है आपका, इसका जो एंगल है, दिस इज वी कॉल्ड एज ए साइड कटिंग एज एंगल ASA में। तो ये जो अल्फा है, ये बेसिकली जो हमने बात की ASA का मेजरमेंट है, और उसको हमने CS से डिनोट किया। नाउ लेट्स गो टू द ऑर्थोगोनल रेक सिस्टम। ORS सिस्टम में सेम एज का एंगल आप कहां से लेते हैं? ये जो मशीन प्लेन होता है बेसिकली, जो कि लॉन्जिट्यूडनल प्लेन बोल सकते हो इसको, मशीन लॉन्जिट्यूडनल प्लेन बोल लो, या एक्सिस ऑफ द वर्कपीस बोल लो, इसको बहुत ही सिंपल लैंग्वेज में बोलना है। वहां से जो मेजरमेंट करते हो उसको हमने नाम दिया है व्हाट। तो ये जो मेजरमेंट है इसका, वो कहां से होगा? इसकी एक्सिस ये है, और इसकी एक्सिस का मतलब हॉरिजॉन्टल लाइन से अगर मैं बात करूं तो ये वाला जो एंगल होगा, ये, इसको मैं हटा देता हूं, ये तो CS यहां से था, CS वाज फ्रॉम हियर, तो और इससे जो इस एज का एंगल है, ये इस लाइन से जो एज का एंगल है, वो बेसिकली उसमें हम उसको लैम्डा डिनोट करते थे। वो है कौन सा? वो ये है, हटा देता हूं इसको। वो कौन सा? ये लाइन। तो इससे इसको मैं हॉरिजॉन्टल को एक्सटेंड किया, या उस केस में इसने ये लिखा हुआ है, ये बात एक ही है। सो दिस हॉरिजॉन्टल से इसका जो एंगल है, ये एंगल क्या है? दिस इज ए, वी कॉल दिस एंगल लैम्डा, और यहां पर उस एंगल को उसको थीटा डिनोट किया उसने। सो दिस वाज व्हाट वी कॉल लैम्डा, एंड वी वर सेइंग दिस वाज द इन ORS, एंड वी आर सेइंग दिस इज द प्रिंसिपल कटिंग एज एंगल। बात है, एज वही है, फर्क ये है कि रेफरेंस अलग है, तो रेफरेंस यहां से है। तो दिस इज लैम्डा, दिस इज अल्फा, दैट्स ऑल। सो ये जो आपका जो एंगल है, सो इसीलिए आपने देखा होगा इसमें अगर आप बात करोगे समथिंग, इट बिकम्स दिस वे, ट्राइंगल बन जाता है ये, तो ये हो जाता है आपका लैम्डा, और ये हो जाता है अल्फा, राइट। सो 180, तीनों को मिला दो, वी से दैट लैम्डा प्लस अल्फा इज इक्वल टू लैम्डा प्लस CS इज इक्वल टू 90 डिग्री। दिस रिलेशनशिप यू मस्ट हैव सीन। तो इस केस में क्या हो गया? वो मतलब 180 माइनस जो तीनों का एंगल है, दैट इज अल्फा प्लस, सॉरी इसको अल्फा मैं बोल रहा हूँ, CS बोल लो, CS प्लस लैम्डा प्लस 90 क्या होना चाहिए? 180 होना चाहिए। यही हुआ, ये अल्फा, ये लैम्डा, और ये 90। सो CS प्लस लैम्डा क्या होगा? दैट इज 90 डिग्री। ठीक है। सो एनीवे, नाउ ये रिलेशनशिप आपको ऑलरेडी पता है, ये आपने देखा भी होगा, स्टडी भी किया होगा। सो दैट इज हाउ इट इज। बट एनीवे, सो द सेम एज, दिस इज ORS सिस्टम। सो इसका मतलब है प्रिंसिपल कटिंग एज एंगल कौन सा? थीटा, जिसको हम लैम्डा बोल रहे हैं, ये, एंड साइड कटिंग एज एंगल। तो सेम एज के लिए जो नाम दिया हमने साइड कटिंग एज एंगल, ये ऐसे। सो D इज गोइंग टू बी द करेक्ट ऑप्शन। क्लियर? सो ये क्लैरिटी होनी चाहिए आपको, एंगल मेजरमेंट कैसे है, कहां से आता है सेम एज के लिए। D, गो एड। A twist drill has the following number of cutting edges. A twist drill has the following number of cutting edges. तो इसके लिए ट्विस्ट ड्रिल का आपको जो है वो शेप पता होनी चाहिए। You must have the idea of the twist drill. How does it look like? Right. So ये आपकी ट्विस्ट ड्रिल है। You must have all these, right? तो प्रिंसिपल कटिंग एजेस या मेन कटिंग एजेस कौन से होते हैं? एंड में होते हैं, ये वाला, ये मेन कटिंग एजेस, ये प्रिंसिपल कटिंग एजेस हैं एंड में। और ये पॉइंट एंगल है, जिसको हम पॉइंट एंगल या यहां ले लो या यहां ले लो, ये पॉइंट एंगल बोलते हैं हम, जिसको हम 2 बीटा से भी डिनोट करते हैं व्हेन यू आर सॉल्विंग द न्यूमेरिकल्स। एनीवे, एंड देन यू आर हैविंग ए फ्लूट। ये फ्लूट है आपकी, पर्पस आपको पता है, कटिंग फ्लूट प्रोवाइड करना, और जो चिप का रिमूवल है दैट कम्स आउट ऑफ दैट फ्लूट। एंड जो फ्लूट के आपके एंड होते हैं ना, ये वाला, ये जो कटिंग एजेस होते हैं, तो दीज आर कॉल्ड एज सेकेंडरी कटिंग एजेस। सो मेन कटिंग एक्शन इज परफॉर्म बाय द मेजर कटिंग एजेस, एंड द सेकंड एक्शन जो है वो आपका कौन करेगा? सेकेंडरी कटिंग एजेस, ये वाले जो फ्लूट के ऊपर होते हैं, दे विल परफॉर्म। सो वी आर हैविंग 2 टाइप्स ऑफ एंगल्स ओवर हियर। गो अहेड। shows a part of the slab milling cutter, या peripheral milling बोल लो या slab milling cutter बोल लो. Part A, B, C are called. A part कौन सा है, B part कौन सा है? ओके गुड. सो सी द ज्योमेट्री ये आपके पास है, ये आपका मिलिंग कटर है, और इस मिलिंग कटर का आपका इफ यू सी दिस इज बेसिकली व्हाट वी कॉल एज, ये पॉइंट तो आपका कटिंग एज हो गया, राइट. ये फिलेट पोर्शन है बीच में, क्लियरेंस एंगल आपका दिया. इसको अगर मोर एप्रोप्रिएटली थोड़ा सा और देखना है तो ये थोड़ी सी ज्योमेट्री बेटर रहेगी इन टर्म्स ऑफ, जहां पे क्लियरेंस एंगल की बात आएगी वहां पर थिंक ऑफ इट लाइक ए फ्लैंक सरफेस. सी इन केस ऑफ सिंगल पॉइंट कटिंग tool also, you know, you are having the flank surface, right? So you are having a flank surface. So flank surface को हमने inclination दी थी, we used to call it as a clearance angle also. So flank angle, clearance angle, relief angle. So that means when we are talking about relief or clearance, it means it is related to flank surface. So over here top वाला तो बिल्कुल आपका जो है ये land surface हो गया, but इफ यू सी कटिंग एज कहां है, कटिंग एज ये तो मैंने बात कर ली, उसमें ये कटिंग एज आ गया. ये वाला जो पोर्शन है ये क्या है, आपका फेस है, ये वाला, दिस वन, दिस इज फेस, ये दिस फेस. अगर ये फेस है तो दूसरे वाला क्या होगा, पीछे वाला उसका क्या रहेगा, फ्लैंक रहेगा. ये वाला पोर्शन जो है ये फ्लैंक रहेगा आपका. तो ये फेस हो गया, ये कटिंग एज हो गया, ये आपका जो है इसके ये वाला पोर्शन जो है वो क्या हो गया, फ्लैंक हो गया. एंड उस फ्लैंक के लिए इसने जो है यहां पर लाइक क्लियरेंस एंगल्स भी मेंशन करके रखे. एंड रेस्ट आल्सो यू शुड हैव द आइडिया, जो थोड़ी बहुत और टर्मिनोलॉजी है वो भी आप इसकी देख सकते हो, बट एज ऑफ नाउ आई थिंक वी विल डिस्कस ओनली दैट मच. सो इफ यू गो अहेड विद दैट देन वी आर लेफ्ट आउट विद दिस वन. सो ये वाला पोर्शन तो आपका फेस हो गया, कटिंग एज हो गया, और ये वाला पोर्शन आपका फ्लैंक हो गया. सो कटिंग एज ABC उसी सीक्वेंस में, कटिंग एज फेस B पोर्शन एंड देन C एज ए flank, right? Okay, let's go ahead. Consider the following statements. Go ahead with this and try to draw some kind of inference from this. Consider the following statements. A large rake angle means lower strength of the cutting edge. अगर कई बार डाउट आ जाए आपको तो इमीडिएटली ड्रॉ कर दिया करो फिगर. आई थिंक इट बिकम्स प्रीटी इजी. ये सिंपल ऑर्थोगोनल कटिंग ऑपरेशन है, यू ऑलरेडी नो. सो दिस इज रेक एंगल अल्फा. सो बोलता है इफ रेक एंगल इज लार्ज, लार्ज रेक एंगल मींस लोअर स्ट्रेंथ ऑफ द कटिंग एज. ऑब्वियसली लेट्स से मैं इसको बढ़ा देता हूं. ओके, आई एम इंक्रीजिंग इट. तो मैंने क्या टूल को ऐसा टूल लिया, ये टूल ले लिया. सो आई इंक्रीज द कटिंग एज, oh sorry, this alpha. So if I am increasing the alpha, the material at the tip will become less. If it is less, then obviously it will become weak. Lower strength of the cutting edge, क्योंकि मटेरियल यहां पर जो टिप पे क्या हो रहा है, कम हो रहा है. When I am increasing the alpha, alpha 1 से मैंने alpha 2 कर दिया. Let's see. So this statement is correct. Cutting torque decreases with the rake angle. Now see, ये थोड़ा सा आपको indirectly inference draw करना पड़ेगा. Reason being that when we increase the rake angle, shear plane angle also increases. Let us say ये जो अल्फा है इसके corresponding मैं इसको, when you are having this plane, I will say this is phi 1. So when you are having rake angle alpha 1, I am having shear plane angle this one. So when I will increase this rake angle, shear plane angle will also increase. ये so ये alpha phi 2 बोल दो. So whenever you are having a cutting torque decreases with rake angle, हाँ जब मैं मतलब with rake angle I am increasing the rake angle. So if I am increasing the rake angle, then shear angle increases and the shear area will decrease. पहले shear area यहां से लेके यहां तक था, मतलब एक डायमेंशन, दूसरी विड्थ थी, विड्थ तो दोनों केस में सेम ही रहेगी. सो दिस वाज दिस मच, ये लेंथ इतनी थी. अब मैंने जब इसका एंगल बढ़ाया तो ये एंगल जो shear plane एंगल इतना होगा, इसका मतलब जो shear एरिया की एक डायमेंशन है ये कम हो गया. इसका मतलब ओवरऑल shear एरिया क्या हो गया, कम. विड्थ तो उतनी है इस केस में भी, इस केस में भी, बट जो इसका जो लेंथ है shear plane की वो कम होगी. If this shear plane has reduced, इसका मतलब है shear area कम हो गया, the amount of force that you need to apply to cut that material will get reduced. So power consumption कम होगी. तो shear अगर force कम करनी पड़ेगी तो obviously torque that you apply need to apply to cut the same this shear plane, or so, not same shear plane तो change होगा. This material will get reduced. So you can talk this in terms of power. मतलब अगर रेक एंगल बढ़ाओगे तो shear plane एंगल कम होगा, तो shear area कम होगा, shear area कम होगा तो power required will be less. If power required is less, torque required will be less. Cutting torque decreases with the rake angle. That is how you have to relate. So this cutting torque, you just try to relate it with respect to the cutting power or the force. Then only I think you will be able to interpret it. And ये जो कहां से आया, I think वहां से आ जाएगा 2 plus beta minus alpha. क्या आया ये 2 plus beta minus alpha is equal to कितना 90 है, merchant first circle. तो if I need phi, तो phi उस तरफ ले जाओ तो आपका बीटा माइनस कितना हो गया 45. चलो इसको, और ये माइनस बीटा by 2 plus alpha by 2, so phi. So if I let's say don't talk about this, simply अगर मैं अल्फा इंक्रीज करता हूं, सॉरी हाँ अल्फा इंक्रीज करता हूं तो phi भी क्या होगा, इंक्रीज होगा. ठीक है, वहां से मैंने रिलेशन लिया. दैट इज अ मर्चेंट फर्स्ट एनालिसिस, राइट. यू आर हैविंग दिस रिलेशनशिप. सो अगर अल्फा इंक्रीज करूंगा तो आपका shear plane एंगल भी इंक्रीज होगा. व्हाट? ओके. सो दैट मींस सी इज गोइंग टू द करेक्ट ऑप्शन, बोथ 1 and 2. Okay, go ahead with this. So you're having, which of the following are the machinability criteria? Now see, point is machinability. When we talk about the machinability, we are talking about how easy for us to cut a material. कितना आसान है मुझे material को cut करना. We talk that way. So to do that, we have different ways of getting that idea. One could be, अगर मुझे कम फोर्स अप्लाई करनी पड़ रही है उसको सेम अमाउंट ऑफ मटेरियल को रिमूव करने के लिए, तो मैं बोलूंगा इट इज इजी फॉर मी टू कट इट. या कम पावर यूज करनी पड़ रही है टू cut that material, same amount of material, I will say it is easy for me to cut that material. Or if I'm getting better surface finish, keeping all the other parameters same, I will say better machinable material. आसान है उसको machine करना. So I could have different ways through which I can, or I can say in terms of tool life also, for the machining the same amount of material, if I'm getting better tool life in terms of time, then I will say it is better machinable material. So whether you talk in terms of tool life, whether you talk in terms of surface finish, or whether you talk in terms of cutting force, you have to relate it with the power. If more the power, less the power it is consumed, then obviously less amount of force that you may be applying, right? So that means all of these I can represent this machinability in terms of tool life also, cutting force also, in terms of surface finish. Better machinable material is one where tool life is better, cutting forces are less, surface finish is very good. Good. So that is how. So I think A 1 2 3 all are going to be the. Just see this. Go through this one. Which of the following are the limitations of powder metallurgy? High tooling and equipment cost, wastage of material, it cannot be automated, expensive metallic powders. C means 1 and 4. You're saying C. Okay, let's see them one by one. With the following are the limitations of powder metallurgy. Now see, high tooling and equipment cost. Why do we have do we have the high tooling and material cost, equipment cost? Yes, because I have to compress that powder. Because in powder metallurgy, we bring the powder and then we compress it. So obviously tooling cost and equipment cost is going to be high. So this is correct. Wastage of material. You are simply bringing the powder and compacting it. That's all. Where is the wastage of material? It's not like a machining process where you are wasting material. So no wastage of material, very little wastage of material. It cannot be automated. Limitations बोल रहा है वो. It cannot be automated. No, it can be automated. मशीन है, उसको आप ऑटोमेट कर दो, क्या दिक्कत है? So it means ये जो है लिमिटेशन है, it cannot be automated. ये लिमिटेशन नहीं है इसकी. It can be automated. Okay, so and expensive, you are having expensive metallic powders. Now एक्सपेंसिव मेटलिक पाउडर, सी देखो आपने जो है कंपोनेंट बनाना है, जिस रॉ मटेरियल से बनाना है, फर्स्ट क्या करूंगा मैं, माइनिंग करूंगा, एंड आफ्टर माइनिंग आई विल क्रश इट एंड देन आई विल चेंज इट टू अ फाइन पाउडर. सो वो अपने आप में एक चैलेंज है, मतलब काइंड ऑफ ओवरऑल कॉस्ट बढ़ा देगा वो, राइट? सो instead of just simply putting it in the blast furnace and all the melting and all that, so पाउडर बनाना, yes you can say that way, मतलब पाउडर में कन्वर्ट करना आपके लिए कॉस्टली है. रॉ मटेरियल लिया, फिर उसको रिफाइन किया, देन पाउडर फॉर्म में कन्वर्ट किया, और लेट अस से फिर कहीं ट्रांसपोर्ट करना है आपको, तो ट्रांसपोर्टेशन हैज टू बी वेरी एफिशिएंट इन टर्म्स ऑफ कि आपका कहीं उसको कंटेमिनेशन ना हो जाए, इट मींस प्योर एज इट इज. सो वो सारी चीज क्या करती है, ओवरऑल कॉस्ट उसकी बढ़ा देती है. तो एक्सपेंसिव मेटलिक पाउडर्स जो है वो है. तो एक्सपेंसिव मेटलिक पाउडर ये लिमिटेशन है, ये टूलिंग कॉस्ट इसकी लिमिटेशन है. वेस्टेज ऑफ मटेरियल इट्स नॉट लिमिटेशन, राइट? सो मेरे पास अगर आंसर आएंगे तो क्या आएंगे, 1 and 4. सो वेस्टेज ऑफ मटेरियल, नो, देयर इज नो वेस्टेज ऑफ मटेरियल, वेरी लेस मटेरियल एस्टिमेट, एंड कैन नॉट बी, इट कैन बी ऑटोमेटेड. तो ये तो दो वैसे ही रूल आउट हो गए. क्लियर? yes. Okay, I think maybe yes you are having that way कि आपके पास different methods हैं. मतलब ये तो जस्ट मैंने वन ऑफ द वे बताया आपको, क्रश कर रहा हूँ ऑल दैट कर सकते हो, बट ओवरऑल जो भी मेथड आप यूज करोगे उसको, चाहे आपकी क्या कहते हैं एटॉमिक लेवल पे बात करें हम उसको सेपरेट करने की, तो ओवरऑल कॉस्ट आपकी जो वो ज्यादा रहेगी. ठीक है? How is the type of railway wheel fitted? Oh, sorry. How is the type of a railway wheel fitted? Basically, the question is how the railway wheel, आपका जो एक कोई particular railway wheel है, how it is fitted? Fit कैसे किया जाता है? किसमें? एक्सेल में. तो आपका जो एक्सेल है रेलवे का, उसमें जो है आपने व्हील लगाए हैं दोनों तरफ से. So how it is fitted? क्या उसकी आप वेल्डिंग कर देते हो या क्लैंप कर देते हो? What you do? So basically it is done by interference fit. Interference fit आपको पता है, already you may be knowing. So that is since you are having this wheel, okay, तो मैंने क्या करना है, you are having a wheel and in this wheel you are having a hub, hole हो गया ये, and you have to fix it on the shaft. That means in this case ये axle हो गया. So if you want to fix it, so what we do is हम क्या करते हैं, इसको जो है थोड़ा बड़ा बनाते हैं. किसको? शाफ्ट विल बी मेड लिटिल लार्जर देन द डायमेंशन ऑफ द होल. जो होल का डायमेंशन है उससे थोड़ा सा बड़ा बनाएंगे और फिर क्या करेंगे, उसको पुश फिट करेंगे. सो विल डू, तो उससे क्या होगा, क्या अगर बड़ा होगा ये, तो आप क्या करोगे, इसको काइंड ऑफ यू हैव टू पुश इट हार्ड इन ऑर्डर टू फिक्स दिस ऑन दिस, और ये रोटेट नहीं कर पाएगा फ्री, बिकॉज फ्रिक्शन बहुत ज्यादा हो जाएगी आपने उसको मटेरियल को. सो दिस इज डन बाय द इंटरफेरेंस फिट. सो इन इंटरफेरेंस फिट क्या करते हैं हम, शाफ्ट का डायमेंशन हमेशा क्या होता है, बड़ा होता है विद रिस्पेक्ट टू द दैट होल. सो होल का जो डायमेंशन है उससे बड़ा बना दो इसको. सो दैट इज सेम हैज बीन शोन यू ओवर हियर. सो इफ आई वांट टू प्रोड्यूस द इंटरफेरेंस फिट, देन शाफ्ट हैज टू बी इन एनी केस लार्जर देन द होल डायमेंशन. सो सेम इज डन ओवर हियर. शाफ्ट को थोड़ा सा बड़ा बना दिया और उसको जो है वो tightly fix करके जो है, then we can have an interference fit, and that way it cannot rotate because this lot of friction over there between these two surfaces, and plastically they have been joined together. इसको देखो, just go through it. Trimming is the process associated with. चेक करो इसमें कौन से में कहां जरूरत पड़ेगी हमें ट्रिमिंग की. ओके, नाउ इन सारी प्रोसेसेस में इलेक्ट्रोप्लेटिंग में ट्रिमिंग कहां करूंगा, वो तो प्लेटिंग कर रहा हूं मैं सिंपली उसके ऊपर, सरफेस के ऊपर. अल्ट्रासोनिक मशीनिंग, वो तो अपने आप में मशीनिंग प्रोसेस है. ट्रिमिंग की बात करेंगे, दैट इज ऑल्सो ए मशीनिंग प्रोसेस, राइट, व्हिच वाज यू आर सेइंग फ्लैश, टंगस्टन इनर्ट गैस वेल्डिंग, ये तो वेल्डिंग प्रोसेस है, राइट. सी, दिस इज व्हाट द सेम थिंग दैट यू आर मेंशनिंग. सो फॉर एग्जांपल, अगर मैंने इसको मटेरियल को बनाया, देन आई एम गोइंग टू हैव ए फ्लैश, whether it is a closed die forging operation or sometimes definitely your this impression die forging in case it is going to be over there. So जो फ्लैश है आपका, ये पार्ट मैंने बनाया, तो जो पेरीफेरी में मटेरियल होगा उसको जो है मुझे रिमूव करना है, वी कॉल इट एज ए ट्रिमिंग प्रोसेस, कटिंग प्रोसेस है वो. तो इसलिए ये जो रहेगा आपका फोर्जिंग में रहेगा. फोर्जिंग में वी मे हैव टू, impression die forging में तो in any case it is going to be there, and in case of a closed die forging operation it may or it may not be, right? So that is the meaning of this. Just see this. The cutting speed of a tool refers to yes, see, you already maybe having the idea different velocities that we have in a cutting process, and there you may be knowing already. For example, again मैं वही आपका simple cutting operation ले लूं, so you are having different velocities over there. So velocity of the tool with respect to the workpiece, cutting velocity. Velocity of the chip with respect to the tool, workpiece. Velocity of the chip with respect to the workpiece, shear velocity. Velocity of the chip with respect to tool, chip velocity. So ध्यान रहे, different types of velocity you need to have. Cutting speed, cutting velocity is what? Velocity of the tool with respect to the workpiece. So यही है, बता रहा है कि rate at which cutting edge, मतलब cutting tool passes over the surface of the workpiece, that means with respect to workpiece. So you're going to have D as the correct option. Okay, anyway, I have already explained you. Go through this. Okay, see, why not 1 and 2? Higher cutting forces, are these two the same? अगर मैं आपसे क्वेश्चन पूछूं, are these two the same? क्या ये स्टेटमेंट दोनों की, क्या ये और ये बात एक ही है? Obviously, you know, smaller shear angle, यही मैंने आपको एक्सप्लेन किया अभी. Smaller the shear angle, more the power, more cutting force. तो ये जो हायर कटिंग फोर्स और बोल रहा है स्मॉलर शेयर एंगल, क्या है? स्मॉलर शेयर एंगल मतलब लार्जर कटिंग एरिया, एंड मोर पावर मीन मोर कटिंग फोर्स दैट यू हैव टू अप्लाई. इसका मतलब ये और ये तो बात एक ही है. इस केस में क्या होगा? मशीनेबिलिटी कम होगी बिकॉज यू आर कंज्यूमिंग लॉट ऑफ पावर टू मशीन द सेम मटेरियल. वेयरएज लॉन्गर टूल लाइफ, मतलब सेम मटेरियल अगर आप ऑब्टेन करने के लिए मटेरियल रिमूव करते हो उसके लिए लॉन्गर लाइफ मिलती है तो इट्स क्वाइट गुड, राइट. लार्जर शेयर एरिया सेम थिंग एंड बेटर सरफेस फिनिश. तो बोथ आर द क्राइटेरिया. तो लॉन्गर टूल लाइफ अगर मुझे मिलती है, बेटर सरफेस फिनिश मिलता है, तो आई कैन रिप्रेजेंट ओके better that machinable, the material is more machinable, easy to machine for us, right? So it means you're going to have D as a correct option. Okay, go ahead. Tool life may be measured by okay, I think it's quite good. So see, कोई भी तरीका है, any of these methods I can follow to tool life. या तो मैं ये बोलूं कि देखो कितना टाइम. tool life does not mean in terms of time. tool life का मतलब है कि when I'm using that tool, how many more number of parts it can produce. पहले 10 करता एक टूल है, सेम मटेरियल का, एवरीथिंग सेम, सो इट इज प्रोड्यूसिंग 10 पार्ट्स, अदर इज प्रोड्यूसिंग 20 parts. I will say it is having the tool which is producing 20 parts of same quality. I will say it is a better tool, or it is having more tool life. So I can time in terms of time of the tool कि मैंने कितना कॉन्ट्रैक्ट, 2 घंटे तक, 10 घंटे, तो ये टूल यूज कर रहा हूँ 10 घंटे तक यूज कर सकता हूँ while cutting. So obviously that will also quantity of material removed. कितना क्वांटिटी, एक टूल, 2 टूल लेता हूँ, one tool which is removing more material, so I will say it is having a better tool life. Or in terms of number of workpieces it is producing, then also, or time for the flank wear, or in terms of wear also. Rather, this is the most practical method of for the that operator to find out whether that life is almost going to be over. Number of, देखो मैंने अभी 10 पीस को निकाला, कल फिर एक पीस और लाया, एंड समथिंग, इट इज वेरी डिफिकल्ट फॉर हिम टू कीप द ट्रैक ऑफ द टाइम, एग्जैक्टली कितने नंबर ऑफ घंटे मैंने टूल को चलाया. So it is not something continuous activity that I am performing, but in terms of amount of wear it becomes very easy. So that is why आपका जो flank wear that becomes very important. Sorry. So कि अगर मुझे पता है कि इतने अमाउंट से wear हो जाती है, let's say this is the amount of wear, let's say I'm saying that this much, let's say any random value I'm taking, let's say अगर 0.75 mm की wear हो जाएगी flank के ऊपर, then it will start producing अनसेटिस्फैक्टरी पार्ट, क्वालिटी पार्ट प्रोड्यूस नहीं करेगा. सो इफ दैट बी द केस, तो उसके लिए क्या करते हैं ऑपरेटर के लिए, इट बिकम्स वेरी इजी दैट बिकॉज ऑन डेली बेसिस व्हेन ही इज यूजिंग, तो उसको आइडिया है कि 0.75 mm जो है रफली कितना है. सो व्हेन इट इज रीचिंग, लेट्स से इट इज रीचिंग दिस मच wear has taken place, you will get the idea, okay, almost it is going to, this life is going to be over, I have to send it for regrind. So practically when I have to use make use of this tool life concept, I think wear is the very common way to make use of this concept. So it is late time for flank wear to reach a certain dimension. वो depend करेगा टूल के ऊपर कितना, 0.7 mm, 1 mm, whatever, right? उतने, if it is within that wear, तो if that much flank wear is within that, then it will produce satisfactory parts. It is, he is not going to bother about that. But हाँ, उसके आसपास आगे तो he will be मतलब he will become alert that it will start producing bad parts अगर वो ड्यू केयर नहीं करेगा उस वक्त, या उसको रिग्राइंडिंग के लिए नहीं भेजेगा. तो गो अहेड, go through this. Straight grades of cemented carbide cutting tool materials contain. Straight grades का मतलब है कि cemented carbide, he as a principal cutting tool material, that is the meaning of straight grades. cemented carbide being used as a only one particular type of carbide. If I have to reframe it, ऐसे बोल सकते हैं, if one particular type of carbide if I am using as a tool material, तो उसको straight grade बोल दिया, we call it as a straight grade. Now see, straight grades of cemented carbide cutting tool materials contain, इसका मतलब है cemented carbide में आपके अलग अलग टंगस्टन कार्बाइड हो सकता है, टेंटलम कार्बाइड हो सकता है, टाइटेनियम कार्बाइड हो सकता है. स्ट्रेट ग्रेड में you will say either tungsten carbide, you will say either or you can say tantalum carbide or titanium carbide. तो अगर मैं इनमें इंडिविजुअली किसी का भी एक टूल बनाता हूं, then I will call it as a straight grade. Cutting tool materials contain what? See, always keep in mind these tools which are having a very high hardness and strength, so their base material is going to be very strong. और उस बेस मटेरियल को अगर बनाना है तो यू आर हैविंग सम लिमिटेड मेथड्स थ्रू व्हिच यू कैन मेक, एंड मोस्टली एक जो पाउडर मेटलर्जी टेक्निक में यूज की जाती है, वेयर पर्टिकुलर सिरामिक्स टूल्स हो गए, तो सिरामिक के पार्टिकल्स लेंगे और उसको पाउडर मेटलर्जी की टेक्निक के थ्रू कॉम्पैक्ट करेंगे, एंड देन वी विल मेक देम. सेम इज गोइंग टू हैपन फॉर द कार्बाइड टूल्स आल्सो, बिकॉज जो कार्बाइड्स हैं दे आर हैविंग ए वेरी हाई मेल्टिंग टेम्परेचर, राइट? सो वी कैन नॉट melt them because it becomes difficult for us to melt them to obtain such a high temperature. तो हम क्या करते हैं, पाउडर मेटलर्जी में एक मेथड अडॉप्ट करते हैं कि एक दूसरा मटेरियल ऐड कर देते हैं which is having a lower melting temperature compared to that original material of which that tool has to be made. So for example इस केस में let's say tungsten carbide ले लेता हूं, तो उसके पार्टिकल्स को मिक्स करूंगा और कॉम्पैक्ट करूंगा, they will not join together because मैं उतना टेम्परेचर ले जा, I cannot raise the temperature that high. So what I will do, I would add some other material like cobalt. इस केस में कोबाल्ट को ऐड किया तो कोबाल्ट का टेम्परेचर इज सिग्निफिकेंटली लो कंपेयर टू दैट कार्बाइड पार्टिकल्स. सो कोबाल्ट क्या करोगे, जब वी विल रेज द टेम्परेचर ऑफ दैट होल मिक्स अप टू द मेल्टिंग पॉइंट ऑफ दैट पर्टिकुलर कोबाल्ट, तो वो क्या करेगा, बाकी पार्टिकल्स को क्या करेगा, पकड़ लेगा. सो इट विल एक्ट एज ए बाइंडर. सो दैट इज व्हाई इफ यू से स्ट्रेट ग्रेड जितने भी होंगे उनमें हम क्या करेंगे, कोई जरूरी नहीं है कि टंगस्टन कार्बाइड हो, और भी कार्बाइड हो सकता था, बट इस केस में क्या टंगस्टन कार्बाइड ओनली नहीं यूज कर सकते, बाइंडिंग मटेरियल चाहिए, बिकॉज आई कैन नॉट रेज द टेम्परेचर टू दैट लेवल. टंगस्टन कार्बाइड और टाइटेनियम कार्बाइड दोनों को मिला दिया, बात तो एक ही है, दोनों का बोथ ऑफ देम आर गोइंग टू हैव अ वेरी हाई टेम्परेचर, सो हाउ आई एम गोइंग टू बाइंड देम. टंगस्टन कार्बाइड एंड कोबाल्ट कार्बाइड नहीं यूज करते हम, अगर कोबाल्ट का कार्बाइड बना दिया तो एक और दिक्कत क्रिएट होगी. सो व्हाट वी विल डू, we will take either tungsten carbide or we will take either titanium carbide or we will take tantalum carbide, whatever, and we'll add the cobalt. So I can get that particular tool through the method of powder metallurgy. Okay, so C is going to be the correct option. Go through this. Almost मुझे लग रहा है थोड़ा सा जो मैंने एक्सप्लेन किया उसी लाइन पे you're going to have this one also. Which aspect is not true in the context of ceramic cutting tools? Okay, any answer? Okay, see which aspect is not true. इसका मतलब let's see which one is true for these. So are made by cold pressing of aluminum oxide powder. Obviously जो सिरामिक टूल है हम जो पाउडर मेटलर्जी टेक्निक से यूज करेंगे बनाएंगे, are in the form of tips. ध्यान रहे जितने भी खासकर जो टूल्स which are made up of hard material, they are in the form of inserts, और जिसको हम टिप्स भी बोल देते हैं. टिप्स फॉर एग्जांपल इट कुड हैव एनी शेप, ट्रायंगल शेप की हो सकती है, रेक्टेंगल की हो सकती है, स्क्वायर शेप की हो सकती है, समथिंग. और यहाँ पर क्या होगा, इसको ये इंसर्ट है, यहाँ होल होगा और उसको फिक्स करना पड़ेगा मुझे. बेस मटेरियल आई हैव टू टेक ऑफ सम बिकॉज इट इज वेरी ब्रिटल है तो टूट जाएगा एकदम, इंपैक्ट लोड आएगा. सो व्हाट विल डू, विल फिक्स इट ऑन द सम मटेरियल, बेस मटेरियल, जैसे स्टील हो गया, सो दैट इसकी स्ट्रेंथ सफिशिएंट है टू कट द मटेरियल, हार्डर मटेरियल, वेयर एज इंपैक्ट लोड को कैरी करने के लिए यू आर हैविंग द बेस मटेरियल. सो इस तरह के इंसर्ट्स बोलते हैं हम उनको, आइदर वी कॉल देम इंसर्ट्स और टिप्स बोल देते हैं. शेप्स कुछ भी हो सकती है, स्क्वायर शेप भी हो सकती है, इट्स नॉट समथिंग, ऐसी शेप हो सकती है, ऐसी भी शेप हो सकती है, राइट. सो मुझे एज चाहिए, दैट्स ऑल. So it means this is also correct. Are brittle and have low bending strength. Obviously, very brittle, so will bend and crack immediately. Wear out fast. अब इन दोनों को देख लेते हैं. If wear out fast at high speeds and resist build up edge and produce a good surface finish. See, wear out fast at high speeds. अब इन दोनों में से अगर मैंने चूज करना है, so see, अगर ये हाई स्पीड में, I think we can use a speed of even 250 to something 300 meter per minute, too high speed. Okay, so they don't wear out so easily. That is why we make use of them. Sorry, अगर wear out होते तो we would not have used them. So you find their applications at higher speeds and they can resist that their strength even at, but they are having quite high hot hardness, we can say that way also. So wear out fast, they don't wear out fast basically, and resist build up edge and produce good surface finish. So obviously वो तो produce करते हैं. Build up edge, that means if for example build up edge तब produce होता है कि जब temperature जो है बहुत ज़्यादा develop हो जाता है between those surfaces. So it can resist, मतलब we can operate them at a very high speeds without build up edge getting produced. So इसमें जो as per this is not the true. Rest are true with respect to this aluminum oxide. Okay. Okay, so go to this one now. In a mechanical shaper, go ahead. In a mechanical shaper, the lifting of the tool during the idle stroke is ensured by, you already know, you already know, said that the lifting of the tool during, because in the idle stroke, I need to bring that back, bring that particular tool back, because in return stroke there is no cutting action, right? So I have to bring it back. So we have a clapper box mechanism basically. ये clapper box है, वो क्या करेगा, उसको टच नहीं होने देगा, लिफ्ट कर देता थोड़ा सा, right? We lift it and then bring it back. So this mechanism is used over here so that in return stroke this tool does not rub with the workpiece. So इस तरह कुछ मैकेनिज्म होता है जो हम उसमें यूज करते हैं, right? So you already know, because return stroke we make faster compared to the forward stroke, and return stroke में मुझे जो है टूल को क्या करना है, रब नहीं करने देना, थोड़ा सा मुझे लिफ्ट करना पड़ेगा उसको. Okay, so then this is going to the factual question है, that's all. We are the following is common between shaper and a planer. Go through this one. Common क्या है दोनों में? Both have stationary tool. ऐसा हो ही नहीं सकता. दोनों मैकेनिज्म जो है वो ऑपोजिट काम करते हैं, राइट? फॉर एग्जांपल इन शेपर cutting tool reciprocates, whereas feed is provided to the table. In case of planer, cutting tool is stationary, whereas that table reciprocates, and feed is given to this particular tool in planer. So both have stationary tool. No, shaper में तो reciprocate करेगा ही करेगा. Both have reciprocating workpieces. No, reciprocating workpiece कौन सा है? टेबल जो है प्लेनर में टेबल मूव करता है, so it cannot have. Both are used for cutting keyways, splines and grooves. देखो splines के लिए आपको indexing mechanism चाहिए, which is not possible over here. So ये भी आपका करेक्ट नहीं है. Splines मतलब splines आपका जो है slots बनाएंगे, different slots on the periphery. So then you are having both use single point cutting tool. So है तो tool तो same ही है. For example, whether you use a planer or a shaper, the tool है आपका, that is a single point cutting tool. So if we talk about both of them, then D is going to be the correct option. Okay, so this is common in both of them. Go through this one now. कूलेंट इज नॉट जनरली यूज्ड इन शेपर. जनरली क्यों नहीं यूज करते? लॉजिक होना चाहिए, राइट? You know, in case of a shaper, you have this one. You don't have a continuous cutting action, right? You don't have continuous cutting action. Had it been a continuous cutting action, then obviously you get less time for the heat dissipation. So since you don't have continuous cutting action, उसने cutting की, return stroke free है, right? So that means you will get opportunity. This tool will get opportunity to dissipate the heat. तो इसलिए even you can operate this tool without coolant. So that is why C is going to be the correct option. Cutting operation is not continuous. Usually, देखो टर्म ध्यान रखना, यूजुअली, नॉट ऑलवेज. मतलब वो तो डिपेंड करेगा, और भी फैक्टर बहुत सारे हैं जिसके ऊपर डिपेंड करेगा, बट नॉट जनरली यूज्ड. बट दैट डज नॉट मीन ऑलवेज. आप ये नहीं बोलोगे कि कभी भी यूज नहीं करते. अगर मटेरियल स्ट्रांग है तो मतलब स्ट्रेंथ, इफ द मटेरियल दैट इज बीइंग कट इज हैविंग अ वेरी हाई स्ट्रेंथ, in that case you may require. But just go through this one now. So what it says is indexing of the job in a milling machine is achieved through. Go through this one. इंडेक्सिंग जो है वो कैसे ऑब्टेन करते हैं हम? So see, indexing का मतलब actually, you know, let's say if I have to cut the gears, right? So first what I need to do is I'm going to cut it, this portion I'm going to cut. Once I have cut, then I need to rotate this workpiece, right? When I will rotate this workpiece, so then this portion will come over here and then cutting action will be performed again. So ये जो method है, that means this is performed with the help of an attachment, जो कि क्या करेगा, उसको इंडेक्स करेगा, घुमाएगा उतने अमाउंट से, by a certain amount, so that पहले यहाँ आपका जो गैप क्रिएट हो गया, then you are producing the gears over here, this portion is produced. And this job in case of milling is machine that is indexing, मतलब उसको सेम अमाउंट से हर बार जो है वो रोटेट करना, इस उसको बोलते हैं हम इंडेक्सिंग. एंड दैट इज परफॉर्म बाय ए अटैचमेंट कॉल्ड एज डिवाइडिंग हेड. सो यहां पर हम क्या करते हैं, डिवाइडिंग हेड यूज करते हैं. एन इंडेक्सिंग हेड आल्सो नोन एज डिवाइडिंग हेड इज अ स्पेशलाइज्ड टूल दैट अलाउज द वर्कपीस टू बी सर्कुलरली इंडेक्स. इस तरह कुछ मैकेनिज्म है, उसका यूज करके हम क्या करते हैं, उसको बाय सेम अमाउंट उसको जो है वो क्या करते हैं, इंडेक्स करते हैं. सो दैट सिमेट्रिकल, जैसे मान दिया मैंने जो है वो 12 टीथ चाहिए मुझे उसके ऊपर, या आपने लेट्स से इफ यू हैव टू मशीन ए सरफेस, लेट्स से स्क्वायर हेड, मैंने जो बोल्ट का हेड है उसको मशीन करना है बाय ए सर्टेन अमाउंट. सो पहले आई वांट टू मशीन दिस सरफेस, फिर मुझे क्या करना पड़ेगा, उसको घुमाना पड़ेगा, सो दैट दिस पोर्शन कुड बी मशीन, राइट? सो देयर वी आर गोइंग टू यूज दिस काइंड ऑफ अटैचमेंट्स. सो इन मिलिंग मशीन वी कॉल दिस जॉब इज डन विद द हेल्प ऑफ ए इंडेक्सिंग हेड, जिसको हम डिवाइडिंग हेड भी बोलते हैं. प्लेट होती है जिसमें नंबर ऑफ होल्स होते हैं एंड ऑल दैट, सो उसका यूज करके हम वी डू दैट होल. Go through this one. Soft materials cannot be economically ground due to. Okay, ground mean grinding process. So what is the difficulty that we have in grinding the soft materials? So soft materials cannot be economically ground. क्या दिक्कत आती है while grinding the soft materials? See, जो आपका व्हील है, व्हील के ऊपर आपने जो स्मॉल पार्टिकल्स यूज किए हैं, एंड देयर इज अ सर्टेन गैप बिटवीन दोस पार्टिकल, राइट? एंड व्हेन वी रिमूव, लेट्स से वी ग्राइंड द सॉफ्ट मटेरियल, चिप का साइज बड़ा होगा रिलेटिवली, एंड द साइज, बिकॉज द साइज ऑफ द चिप विल बी मोर, तो ये जो गैप होता है उसके बीच, उसको क्या करेगा, वो फिल कर देगा. क्लॉग मतलब इट विल फिल द गैप, और वहां पर वो स्टक कर जाएगा. दो ग्रेन्स हैं, ग्रेन्स के बीच गैप को भर दिया और वहां पर स्टिक कर गया. हैड इट बीन अ ब्रिटल मटेरियल और दैट मींस अ सॉफ्ट नहीं, हार्ड मटेरियल है, तो स्मॉल चिप्स विल बी फॉर्म, दे विल फॉल अवे, दे विल नॉट क्लॉग सो इजीली. बट सॉफ्ट मटेरियल में बड़ी चिप है, वो क्लॉग कर जाएगी, बीच में फंस जाएगी, एंड देयरफॉर दैट it will make that whole process inefficient because आपने gaps को क्या fill कर दिया. So soft material cannot be economically ground because frequent wheel clogging. मतलब clogging मतलब वो gaps को भर देगा and therefore it will not efficiently cut. तो जो edges, sharp edges हैं और बीच में आपका अगर if you are having that this chip which is embedded, so वो sharp रहेगा ही नहीं, वो blunt हो जाएगा. Something this way, right? ये तो grinding process है. So cutting, so for example these are the cutting edges, right? So यहाँ पर क्या हुआ है, भर गया ये, यहाँ पर clogging कर दी उसने, fill कर दिया इससे. So ये दोनों काट ही नहीं पाएंगे उसको efficiently next round में, right? Something that way. यहाँ पर clogging होगी, यहाँ पर clogging होगी. Let's say this is how it got clogged over here. Now क्या ये edge sharp रहा ही नहीं, edge तो वही है वो, but काट ही नहीं पाएगा इस round में. So इस process को बोलते हैं clogging. Right? So you're having different. See this one. The hardness of a grinding wheel is determined by इसके लिए you need to have the idea of nomenclature of the grinding wheel. That means you must know how the grinding wheel is specified, right? So जो grinding wheel होता है ना आपका, it is attached. grinding मतलब जो grains हैं particularly, ये जो grains हैं, they are bound together. Just you know, the grains, ये जो grains हैं on the wheel, they are bound with the help of some binding material. कुछ binding material use करते हो यहाँ पर इन ग्रेन्स को बेस व्हील से अटैच करने के लिए. नाउ हाउ स्ट्रॉन्ग दैट बाइंडिंग मटेरियल इज विल डिसाइड कि व्हील जो वो हार्ड है या सॉफ्ट है. वी टॉक इन टर्म्स ऑफ हार्ड व्हील एंड सॉफ्ट व्हील. सो हार्ड व्हील एंड सॉफ्ट व्हील डज नॉट मीन द हार्डनेस ऑफ these grains, but it talks about the bonding material, strength of the bonding material that you are using in order to fix those grains with the base material. If that strength is high, then we will say hard wheel. If the strength of the bonding material that you used over here is not that high, then we will say soft wheel, right? Just have a look. The hardness of a grinding wheel is determined by what? Ability of the bond to retain abrasive. ठीक है, ability of the bond to retain. If मतलब a bond strength ज्यादा है, it means it will retain those abrasive particles. That means it is more hard. So it has nothing to do, this term has nothing to do with the hardness of the abrasive grains itself. ये ध्यान रखना. So B is going to the correct option. Which one of the following materials is used as the binding material for grinding wheels? अब ये factual information है, या तो पता है तो ठीक है, नहीं तो नहीं. So now थोड़ा सा idea you can get it from over here. ये जितने भी है ना आपके पार्टिकल्स, फॉर एग्जांपल एल्यूमिनियम ऑक्साइड, क्या है ये? एल्यूमिनियम ऑक्साइड तो यू मे बी नोइंग ऑलरेडी. दिस में भी दिस इज दिस सिरेमिक, राइट? सो एल्यूमिनियम ऑक्साइड हो गया, सिलिकॉन कार्बाइड हो गया, सिलिकॉन कार्ब आई थिंक आई हैव मेंशन्ड ओवर देयर, एल्यूमिनियम ऑक्साइड 2O3, बोरॉन कार्बाइड, ये जितने भी हैं इनके ये दीज आर द ओके. सो दीज ऑल आर द दिस abrasive particles that we use in case of this grinding wheel. And we will discuss one question over there. I have mentioned different abrasive particles over there. So over here sodium silicate is the binding material which we use normally. For example इस grain और इन grains को base material से जोड़ने के लिए ये जो हमने use किया है ये binding material, you could have like rubber, shellac, these kind of materials also, so for binding. So one of them is sodium silicate is also used. Okay, so B is going to be the correct option. Now in grinding wheel a dense structure is required for. Now again you have to see these terms should be very clear to you. Dense open structure and all those things that I am talking about, hard wheel, soft wheel and all that. So for example dense structure, when we talk about, that is how densely those abrasive grains particles are, how close they are to each other, right? So if they are very close to each other, then we will say that is a dense structure. But if gap is more, then we will say open structure. Right? So in grinding wheel, a dense structure is required. तो आपको dense structure का मतलब ये है कि gap उन particles के बीच कम है. Open structure gap ज्यादा है. So from there you can get the idea what kind of material you can grind with that particular wheel. In a grinding wheel, a dense structure is required. कब चाहिए आपको dense structure? क्या ductile material करोगे आप या tough material करोगे? You will go for the अगर dense structure है, gap कम है, and if you go for the tough or ductile material, chip size will be more. Immediately क्या करेगा? Clog कर जाएगा. You will clog it, inefficient बना देगा. So you cannot use dense structure for ductile material and tough materials. ना ही आप उसको हैवी कट के लिए कर सकते हैं. हैवी कट का मतलब डेप्थ ऑफ कट मोर है, साइज ऑफ द पार्टिकल क्या होगा? रिमूव्ड पार्टिकल विल बी मोर. इफ द साइज विल बी मोर, इट मे क्लॉग इट. इसका मतलब हैवी कट्स के लिए भी जा सकते. फिनिशिंग कट्स के लिए जा सकते हो. व्हाई? बिकॉज फिनिशिंग कट में यू विल रिमूव वेरी स्मॉल अमाउंट ऑफ मटेरियल वेयर द साइज ऑफ द पार्टिकल्स विल बी टू स्मॉल. सो वो जो स्मॉल साइज का पार्टिकल होगा वो जो है दो ग्रेन्स के बीच, इवन दो दे आर डेंसली पैक्ड, इट विल नॉट गेट स्टक अप बिटवीन दोस. So we'll go for finishing cut. Okay, same you can interpret. अगर वो क्वेश्चन इस तरह से फ्रेम दे सकता है कि आपका dense structure है, whether you use for brittle material, hard materials or soft materials. So obviously we will use for hard and brittle materials, dense structure. Open structure you will use for gap ज्यादा है, ductile के लिए use कर सकते हो. This question becomes the part of specification. So I hope you may be having a little idea of the grinding wheel specification. वहां से पिक करना पड़ेगा, फैक्चुअल इंफॉर्मेशन है. डेफिनेटली क्वेश्चन आपको आएगा यहां से, इसलिए इसको एटलीस्ट ग्राइंडिंग व्हील स्पेसिफिकेशन का ये पोर्शन कर लेना, वेयर यू शुड हैव द होल आइडिया ऑफ हाउ डू वी स्पेसिफाई एंड ऑल दैट. तो अगर आप देखोगे यहाँ पर, आई वाज मेंशनिंग यू अबाउट दिस सिंबल्स आल्सो, राइट, दैट bond, type of bond material that we use or type of abrasive particles we use, like silicon carbide हो गया, aluminum oxide हो गया, even diamond we make use of. So silicon carbide, only exception over here just you take note of कि silicon carbide को हम C से डिनोट करते हैं, aluminum oxide को A से डिनोट करेंगे. एंड एक्सेप्शन का ध्यान रखना, जो सिंपल है वो तो आपको ध्यान रहेगा. डायमंड है उसको D से डिनोट करते हैं in case of this alphanumeric system of this. And same is the situation over here in case of bond. कौन से मटेरियल का बॉन्ड आपने बनाया है? विट्रीफाइड को V से है, सिलिकेट को S से है, रबर का R है. इसने मेरे ख्याल शैले को होता है E से. I don't know whether I have taken that or not, right? So ये ध्यान रखना. कुछ एक जो एक्सेप्शंस हैं, रेजोनॉइड है, I think it is from B. So those exception you just take note of, right? जो सिंपल है, स्ट्रेट फॉरवर्ड है, वो आप इजीली रिमेंबर कर पाओ. नाउ एक देख लो, इस केस में when we are going for the grade, hard or soft wheel, when we are talking about grade मतलब strength of the bond material. जो बॉन्डिंग मटेरियल यूज किया उसकी स्ट्रेंथ क्या है वो डिनोट करता है ग्रेड. बॉन्ड मटेरियल तो ये डिनोट करेगा यहां पर जो पोजीशन होगी, बट इस पोजीशन में आपका बॉन्ड मटेरियल की स्ट्रेंथ कितनी है. फॉर एग्जांपल उसको डिवाइड किया सॉफ्ट, मीडियम एंड हार्ड. सो एनीथिंग अबाउट Q यू कैन थिंक ऑफ इट एज ए हार्ड व्हील. अगर उसने कोई अल्फाबेट यूज किया लेट से R, सो वी विल कॉल इट एज ए हार्ड व्हील. इफ ही इज यूजिंग लेट से M, वी विल से दिस इज अ सॉफ्ट medium wheel, right? And soft wheel, let's say E, F, D, J, whatever he is using over here. So in this case he has mentioned already, he's talking about the hard wheel. So hard wheel is going to be over there, that is Q2, something this way. So just keep the note of this sequence. Whole of this thing is required to be over there. You can just refer to any book also, it will be clearly given over here. So for me, hard grade grinding wheel will be Q2 Z D. The alternative to a grinding machine is what? Let us say alternative to a grinding machine is what? That means, let us say in some particular case, I want to machine the material which will give me the equally good surface finish or machining characteristics. Which one will I go for? That is the meaning of it. So alternative to grinding machine over here. देखो लेथ आपको ये देखना पड़ेगा कि कौन ऐसी प्रोसेस है जो कि ऑलमोस्ट इक्वली गुड उसके आसपास जो है वो सरफेस फिनिश दे सकती है. तो शेपर सिंगल पॉइंट कटिंग टूल है, यू कैन विल नॉट बी एबल. ग्राइंडिंग इज द पार्ट ऑफ फिनिशिंग प्रोसेसेस. सो ये तो आपको फिनिशिंग प्रोसेसेस में नहीं आता, लेथ अपने आप में नहीं आती, ब्रोचिंग मशीन में नहीं आती. ब्रोचिंग मशीन में आपके पास कटिंग टूल्स. ब्रोचिंग इज ए मटेरियल रिमूवल प्रोसेस, नॉट ए फिनिशिंग प्रोसेस. फर्क यही है कि आपका जो ग्रेजुअली इंक्रीजिंग साइज मल्टीपल एजेस होंगे, ग्रेजुअली इंक्रीजिंग साइज में जाएंगे. मतलब इस ये पोर्शन जो यहाँ एज होगा वो स्मॉल पोर्शन मूव करता जाएगा, थोड़ा और ग्रेजुअली कट करेगा. दैट्स ऑल. सो इफ यू हैव टू टॉक अबाउट, वी विल गो फॉर रिमिंग. एंड you already knowing that reaming is a whole finishing and sizing process. So when we talk about the finishing, that means dimensional accuracy will be quite good, so it can be compared with that of the grinding machine. I hope it is clear. So if I have to do something comparable to that of, so I will go for this one. Which of the following process is primarily used to obtain the surface finish? Right. Vishal, reaming, honing, shaving, all these processes are finishing processes. Which of the following process is used primarily to obtain surface finish? इसमें देख लो आप, होबिंग तो गियर मैन्युफैक्चरिंग प्रोसेस है, राइट. तो दैट डज नॉट मीन कि ये जो आपका बहुत फिनिशिंग प्रोसेस है. दिस इज नॉट अ फिनिशिंग प्रोसेस, दिस इज मेकिंग प्रोसेस. बोरिंग, ये तो बोरिंग तो होल एनलार्जमेंट प्रोसेस है कटिंग टूल. ब्रोचिंग हमने डिस्कस कर लिया. ओके. Honing, I hope he can frame the question from that in the form of like what are the motions involved in honing. For example, जो आपका इंजन का सिलेंडर है, when we have to finish it, we go for honing process. So यहाँ पर you could have something tool यहाँ अटैच किए हैं. मतलब if you see, this is the tool that you are going to have. Now he can talk about the motions. How एक मोशन इस टूल की ऐसे रहेगी, दूसरी मोशन जो है इसकी ये रहेगी. सो ये रोटेट भी करेगा, राइट, एंड अप एंड डाउन भी होगा, राइट. सो इट विल रोटेटिंग, कटिंग, दैट इज वेरी फाइन कटिंग, एंड देन रेसिप्रोकेटिंग आल्सो. सो ये मोशन इन्वॉल्व रहेगी. सो यू कैन फ्रेम द क्वेश्चन फॉर so this is not taper, this is a taper of internal dovetail can be measured with the help of. So for that you need to have idea of internal dovetail. ये आपने लकड़ी में जॉइंट देखा होगा, या you may have seen in the slides also, in machine tool slides also you may have seen, for example lathe also. So this is something structure. So for example इस तरह का जॉइंट जब बनता है, मान लिया लकड़ी में आपने ऐसे बनाया, से वेरी सिंपल. सो इसको हम इंटरनल डवटेल बोलते हैं. ये इंटरनल डवटेल है. व्हाई वी आर कॉलिंग इट इंटरनल? बिकॉज इसने जो है इसके इनर पोर्शन में फिक्स होना है. ये एक्सटर्नल डवटेल है, इसको हम एक्सटर्नल बोलते हैं. ये एक्सटर्नल डवटेल, डवटेल इज दिस जॉइंट. सो इस डवटेल का ये इंटरनल डवटेल है और ये एक्सटर्नल डवटेल है, दोनों को हम ज्वाइन करके ये बनाते हैं. सो व्हेन वी हैव टू मेक ए this measurement of internal dovetail, this is the internal dovetail, then we make use of some kind of balls or rulers, and we make use of slip gauges. So one is the slip gauges that we make use of, and some rollers we will make use of, and then making use of the geometry we basically find out the inclination of this. Clear? So what he is asking us to find out कि अगर internal dovetail है तो how we are going to find out. So we can make use of the balls of standard dimension and slip gauges. इनका यूज करके हम क्या करेंगे, वो inclination we can find out. Okay, clear? So go ahead with this one. Following type of gauges, gauge has the gauging section combined at on one end. So I hope you have the idea of gauges, where we are having different types of gauges that we use. Limit gauges का concept है, that you may be knowing, right? Maximum minimum size को हम use करते हैं to decide whether that part that we have made, whether that fall within those two limits or not, because we cannot make a part with a single limit, right? Difficult, impossible for us to make through any manufacturing process. So there why we are having different. So now see, इस तरह कुछ है कि फॉर एग्जांपल अगर मैंने एक ही एंड में दोनों गेजेस का यूज किया है, फॉर एग्जांपल एक प्लग गेज शो की गई है which is used to check the lower and upper size, maximum minimum size of the, sorry, okay. So for example here if I want to have check the hole whether there is within those two dimensional limits or not, that is a minimum maximum limit, I have those two gauges, one is go gauge and no gauge. So when I am using those two gauges at one end only, so for example here this portion is this diameter is for the go gauge and this is a larger diameter, there is no go gauge. So if it goes inside the hole it will show that okay this is minimum limit se upar hai wo, and if it does not go, no go gauge over here, if it does not go ये इंसर्ट हो जाता बट ये इंसर्ट नहीं होता, इसका मतलब मैक्सिमम लिमिट से नीचे है. सो आई विल से दैट इट इज विद इन दोस लिमिट्स एंड देयरफॉर पार्ट इज ओके. सो एक ही बार में आपको पता चल जाएगा व्हेन यू विल इंसर्ट फ्रॉम वन एंड दैट वेदर दैट पार्ट इज ओके और नॉट, दैट होल दैट यू हैव मेड इज ओके और नॉट. सो दिस वी कॉल्ड एज ए progressive gauges. So you must have combination gauges or progressive gauges. Clear? Okay, so the two slip gauges in precision measurement are joined by slip gauges. मैंने ऊपरी बात की आपके, I just discussed with you the slip gauges which are used for the measurement of that external dovetail, sorry internal dovetail, वहां भी हमने उसको balls के साथ यूज किया. So how do we join them? जब मैंने stack करना है one slip gauge को, slip gauge क्या है, simply जो है वो they are rectangular blocks, very high finish. So how do we do that? So they are the process called as ringing. Ringing में क्या करते हैं, हम एक ब्लॉक लेते हैं मेटल ब्लॉक और उसको क्या करते हैं, नॉट मेटल ब्लॉक, दैट इज ए स्लिप गेज लेंगे और दूसरी स्लिप गेज को पहले क्या करेंगे, जब रखेंगे सो हम क्या कर देंगे, पहले लॉन्जिट्यूडनल मोशन देंगे सो दैट एनी डर्ट व्हिच इज रिमूव्ड फ्रॉम देयर. उसके बाद हम क्या करेंगे, उसको 90 डिग्री में रोटेट करेंगे, ऐसे रोटेट करेंगे एंड व्हेन वी आफ्टर रोटेटिंग एट 90 डिग्री वी ब्रिंग देम बैक, थोड़ा फास्ट मूवमेंट करके उसको यहां ले आएंगे. तो क्या होती है व्हेन विल डू, तो क्या होगा, यहाँ पर वो दोनों क्या है स्टिक कर जाती हैं एक दूसरे से, बिकॉज आपने पार्शियल सक्शन क्रिएट कर दी. कैसे, यहां से तो मटेरियल रिमूव किया आपने, डर्ट वगैरह, और जब मैंने वापस लेके गया जैसे मैंने ऐसे रोटेट किया तो जो एयर है दैट विल एक्सपेल्ड और सक्शन क्रिएट होगी और वो क्या दे विल स्टिक टू ईच अदर. सेम प्रोसेस इज अडॉप्टेड व्हेन रिमूविंग. रिमूव करेंगे तो खींचेंगे नहीं उनको, फिर क्या करूंगा मैं, इसको ऐसे घुमाऊंगा एंड देन यू कैन इजीली रिमूव दैट, राइट. सो दैट इज हाउ यू हैव टू डू. सो वी कॉल दैट प्रोसेस एज ए रिंगिंग, रिंगिंग ऑफ स्लिप गेजेस. तो सेम मेथड यहां पर है, पहले उसको जो लॉन्जिट्यूडनल मूव करो, फिर 90 डिग्री में मूव करो एंड देन ब्रिंग इट बैक टू द सेम पोजीशन. The term allowance in limits and fits is usually referred to. Let us say this is a hole. And this is a shaft. So basically when we say allowance between the two mating parts, it is the intentional difference between the maximum material limits of those two mating parts. Maximum material limits. So for example इसकी maximum material कितना हो सकता है, अगर होल में ऐसे, ठीक है, ये टॉलरेंस शो कर रहा हूं, इस केस में दिस इज अ होल, कीप इट इन माइंड. अब आप बोलोगे इसको मैं, इफ आई वांट टू शो, यू हैव क्रिएटेड दिस होल समवेयर ऑन द पार्ट, इसको मैं टॉलरेंस दे देता हूं, इसमें भी टॉलरेंस दे देता हूं एंड दिस इज द पार्ट जिसमें मैंने होल क्रिएट किया, ये लेट अस से इस साइज का ये. सो इसकी मैक्सिमम मटेरियल का लिमिट क्या है, होल की मैक्सिमम मटेरियल, जब मैं व्हेन यू हैव द होल, व्हेन यू हैव द मैक्सिमम मटेरियल विद इट, वो तब होगा जब आपका ये कॉरस्पॉन्ड करेगा इससे. सो होल की मैक्सिमम मटेरियल लिमिट ये है. मिनिमम कब होगी, कम से कम होल में मटेरियल कब लगा होगा, जब सबसे बड़ा होल होगा. मैक्सिमम मटेरियल जो मैक्सिमम मटेरियल होल में कब लगा होगा, जब सबसे छोटा होल होगा. सो दिस इज द मैक्सिमम मटेरियल लिमिट ऑफ होल. एंड व्हाट इज द मैक्सिमम मटेरियल लिमिट ऑफ शाफ्ट, मैक्सिमम मटेरियल शाफ्ट में कब लगा होगा, जब उसमें मैक्सिमम मटेरियल होगा, वो तब कब होगा, व्हेन इट इज हैविंग द मैक्सिमम साइज. और मिनिमम मटेरियल कब लगा होगा, जब ये सबसे छोटा होगा. सो व्हाट आई सेड इज द अलाउंस इज द intentional difference between the maximum material limits of the
मेटिंग पार्ट्स ये दोनों है, इसकी मैक्सिमम मटेरियल लिमिट ये है, इसकी मैक्सिमम मटेरियल लिमिट कौन सी है, ये। सो इन दोनों के बीच का जो डिफरेंस है उसको हमने कहा अलाउंस। है ना क्लियर? सो इफ दैट बी द केस, सो अब देख लो, इसको इंटरप्रेट कर सकते हो। सो डोंट यू थिंक इन दिस सिचुएशन द क्या है डिफरेंस बिटवीन द मैक्सिमम साइज एंड मिनिमम साइज ऑफ द शाफ्ट, difference maximum size and minimum size of the hole, difference between maximum size and minimum size of the hole, I think the maximum clearance, okay, we have to see this way, maximum clearance, max difference of tolerance, no, then you are having the maximum, इस केस में क्या आएगी आपकी, you are going to have the minimum clearance, देखो इस केस में you are going to have the minimum clearance as per this, if you see मिनिमम क्लियरेंस कब आएगी, सबसे छोटा होल सबसे बड़ा शाफ्ट। सो व्हेन यू आर हैविंग द स्मॉलेस्ट होल इट मींस मैक्सिमम मटेरियल इज ओवर देयर, एंड व्हेन यू हैव द मैक्सिमम शाफ्ट लार्जेस्ट मटेरियल इज ओवर देयर। सो स्मॉलेस्ट होल लार्जेस्ट शाफ्ट, तो लार्जेस्ट शाफ्ट यहां से लेके यहां तक होगा, स्मॉलेस्ट होल यहां से होगा, तो क्या होगा ये, दिस इज द मिनिमम क्लियरेंस। सो इस केस में यू कैन से दिस बिकम्स द मिनिमम क्लियरेंस, minimum clearance between shaft and hole. So the option is going to be A option, minimum clearance. That way also you can say, अगर interference के term में बात करनी है तो, but he has not spoken in terms of interference, but anyway that is going to be okay. Clear? So I have not written that over here. So you can say this is A. A is going to the answer. So let us see this question now. The size of the hole and the shaft are respectively this one. So I think this is a calculation part. You can immediately, the best part is in this case is immediately draw the hole and the shaft, depict them, it becomes easy for us to draw. Let's say size of the hole and shaft are represented, so hole का इतना है 20 mm and then this is on the both the sides, right, or one side only. So let's say if I'm this is your hole, right? So on one side it is 20 plus this, right? So let's say this is इसको मैंने ज्यादा ले लेता हूँ, थोड़ा सा कम ले लेता हूँ, so that I'm having, okay, now मैं क्या करता हूँ, ये 20 की लाइन ड्रॉ कर देता हूँ, right? So this becomes 20, यहां से यहां कितना हो गया, ये 20 हो गया। So अब जो होल है that is 20 plus 0.05, तो यहां से यहां तक कितना हो गया, ये 0.05, so 20.05, smallest size क्या है 20.05 and largest is 20.1, that means यहां पर और भी ये जो आपका टॉलरेंस दी है इसने अपने आप ही पता चल जाएगा, इस यहां से लेके यहां तक क्या है, ये 0.05 अगेन। है ना क्लियर? इसका मतलब ये है कि होल का जो कम से कम साइज कितना है, इतना है 20.05 और मैक्सिमम साइज कितना हो जाएगा, ऐड कर दो 20 प्लस दिस 0.05 प्लस 0.05 कितना हो गया 0.1, तो 20.1 ये। नाउ व्हाट अबाउट द शाफ्ट, शाफ्ट की बात करेंगे 20 से नीचे है, बट मैक्सिमम कितना है, मैक्सिमम जो है प्लस है, प्लस का मतलब है 0 पे है ये, जिसका मतलब शाफ्ट जो मेरा है ये यहीं पे लाई कर रहा है मैक्सिमम साइज। मिनिमम कितना है, मिनिमम जो है माइनस 0.05, 0.05 नीचे है, ये टॉलरेंस है, ये इससे इतना नीचे है कितना 0.05 से, सो 0 से नीचे कितना 0.05 mm से। मैक्सिमम कितना 20, मैक्सिमम 20 मतलब ये रेफरेंस लाइन मेरी 20 की है, 20 mm की है, सो ये 20 मैक्सिमम, मिनिमम इतना, दैट्स ऑल। अब जो भी इंटरप्रिटेशन है कर लो, इसमें क्या बोलता है, मैक्सिमम एंड मिनिमम क्लियरेंस इन द असेंबली ऑफ द टू आर एज सिंपल एज दैट। बोलता है मैक्सिमम क्लियरेंस कितनी होगी, मैक्सिमम क्लियरेंस होल सबसे बड़ा शाफ्ट सबसे छोटा, होल सबसे बड़ा कितना है इतना एंड शाफ्ट सबसे छोटा, ये मैक्सिमम क्लियरेंस आएगी, ये 20 की लाइन है। मैक्सिमम क्लियरेंस तब आएगी जब ये होगा, कितना है ये तो देख लो आप साफ है, दिस प्लस दिस, ये यहां तक है प्लस दिस, तो यहां से यहां तक कितना हो गया 0.15 हो गया, ये 0.1 तो यही हो गया, तीनों को ऐड कर दो तो ये आपका कितना होगा 0.15, 0.05 प्लस 0.05 प्लस 0.05, ये मैक्सिमम क्लियरेंस आ गई। तो इसमें से कौन से जाए, या ये है या तो ये, आइदर दिस और दिस। एंड व्हाट इज द मिनिमम क्लियरेंस, मिनिमम क्लियरेंस कब आएगी, जब होल सबसे छोटा बनेगा और शाफ्ट सबसे बड़ा बनेगा। तो होल सबसे छोटा कितना हो सकता है ये, और शाफ्ट सबसे बड़ा कितना हो सकता है यहां तक, इसका मतलब मिनिमम क्लियरेंस कौन सी होगी, ये तो आपके साथ पास साफ ही है, ये कितना है, ये देखो 0.05, so कौन सा है इसमें 0.05. So maximum clearance and minimum clearance you can get it. So particularly in the limits, fits and tolerances, it is advisable जो भी इंफॉर्मेशन है उसको इमीडिएटली ड्रॉ करोगे तो होल थिंग बिकम्स क्रिस्टल क्लियर एंड आप कहीं भी कंफ्यूजन नहीं रहेगा, वेरी इजीली एकदम होल और शाफ्ट को ड्रॉ करो एंड कोई भी इंटरप्रिटेशन व्हाटएवर ही हैज आस्क्ड यू कैन डू इट वेरी इजीली. अगर आप इसको हवा में करोगे ऐसे यहीं से इंटरप्रेट करने की कोशिश, यस यू कैन डू दैट, मैं ये नहीं बोल रहा हूं, बट जब आपका एक काइंड ऑफ एक प्रैक्टिस हो जाती है उसके बाद आप कई बार कर सकते हो, बट इफ यू वांट टू मिनिमाइज द एरर पर्टिकुलरली इन द एग्जाम सेटिंग, बेटर आप क्या करो उसको एकदम ड्रॉ कर लो, इवन दो इफ यू आर एबल टू इंटरप्रेट इट डायरेक्टली फ्रॉम हियर आल्सो, क्रॉस चेक मार लो उसको ड्रॉ करके कहीं गलती तो नहीं हो रही, राइट. सो आई थिंक that is all that we need to discuss. So I hope that is all for today. So in the next session we will be coming up with some other topics. I think in limit, fits and tolerances we can do a few more questions, and from other areas also like gauges also we can discuss more questions, and other areas also within the metal forming or metal cutting also we will take up a few more questions. Okay, so I hope you enjoyed this session. So see you in the next session. Till then, bye. Thank you.